Hello there and welcome to Science for Sleep, where curiosity gets comfortable, complicated ideas slow down a little, and the universe is allowed to be strange without anyone demanding that we understand all of it before bedtime. Tonight, we are staying close to home. Not close in the everyday sense, of course. There will be no short walk, no bus ride, and no sensible pair of shoes involved. We are looking at our own galaxy, the Milky Way, and at something it is doing right now on a scale so large that the whole event can disappear into the background of the night sky. The Milky Way is pulling another galaxy apart. That sounds dramatic, and on human terms it certainly would be. If one object tears another object to pieces, we usually expect noise, panic, paperwork, and perhaps someone asking who is responsible. On the scale of galaxies, though, destruction can be very quiet. Stars do not need to crash into one another. There is no single explosion marking the moment when one galaxy loses a piece of itself. Instead, gravity works over enormous distances and enormous spans of time, gently but persistently changing the paths of stars until a smaller galaxy begins to come apart. The galaxy in question is the Sagittarius Dwarf Spheroidal Galaxy, usually shortened to the Sagittarius Dwarf. It is a satellite of the Milky Way, one of a number of smaller galaxies moving through the gravitational territory of our much larger galactic home. Sagittarius has been interacting with the Milky Way for billions of years, and those encounters have not been especially good for its structural integrity. Each time it moves through the Milky Way's gravitational field, especially during close passages, stars can be pulled away from it. Over time, those lost stars have spread out along its orbit, creating a huge structure called the Sagittarius Stream. When astronomers say stream, they do not mean a narrow little line of stars politely following one another across the sky. The Sagittarius Stream is a vast tidal structure that wraps around the Milky Way, made from stars that once belonged to the smaller galaxy. The stream is so large that, from our position inside the Milky Way, we see different parts of it in different regions of the sky. We are not standing outside our galaxy looking at a tidy diagram. We are inside the thing trying to reconstruct a galactic interaction while surrounded by billions of foreground stars, dust clouds, bright regions, faint regions, and all the other clutter that comes with observing the universe from the middle of a spiral galaxy. It is a little like trying to understand the shape of a forest while standing between the trees, except some of the trees are moving. The forest is hundreds of thousands of light years across, and the map takes years of telescope observations to assemble. So perhaps it is not very much like a forest after all, but we will keep the analogy because it was doing useful work for a moment. Before we go any farther, where are you listening from tonight? Maybe it is late where you are, and the room has finally gone quiet. Maybe it is early evening and you're only beginning to slow things down. Perhaps the sky outside is clear enough to see a few stars, or perhaps clouds, streetlights, curtains, or a neighbouring building have taken care of that for you. Either way, somewhere beyond whatever is outside your window, the Milky Way is continuing this long interaction with Sagittarius. Nothing about it pauses because it is daytime on one side of Earth, or because somebody has misplaced their telescope cap. I would also be curious to know whether you have ever seen the Milky Way clearly with your own eyes. Not just a few bright stars, but that pale, crowded band stretching across a genuinely dark sky. For many people, especially in cities, it is surprisingly difficult to see. Yet that band is our view through the disk of the galaxy we live in. Every ordinary evening on Earth is taking place inside a system large enough to hold hundreds of billions of stars, and that system is still changing. If you find this sort of slow journey through astronomy relaxing, interesting, or simply useful when the day has asked quite enough of you, you can give the video a like and subscribe to the channel. It helps this quiet corner of science reach other people who may also enjoy learning about galactic destruction at a volume suitable for falling asleep. A strange category perhaps, but apparently we have found it. So, get comfortable, let the day become less important for a while, and consider what is happening around us on a much larger scale. We often picture the Milky Way as something finished. A spiral galaxy with a central bulge, a disk, spiral arms, a halo, and a familiar place in astronomy diagrams. There it is, neatly labelled, looking as though someone assembled it long ago and then placed it in space to remain more or less the same. But galaxies are not static objects. They grow, they interact, they absorb smaller systems, their disks bend and ripple. Stars arrive from other galaxies and, after enough time has passed, become almost impossible to distinguish from stars that formed locally. The Milky Way has a history of this kind of behaviour. It did not acquire all of its stars in one peaceful event. Like other large galaxies, it has been built partly through mergers and encounters, taking in smaller systems over cosmic time. Some of those ancient galaxies are gone as recognisable objects, but traces of them remain in the motions, chemistry and distribution of stars around us. Sagittarius is especially useful because its disruption is not merely an event from the distant past that astronomers must reconstruct from a few surviving clues. The process is still visible. There is still a central remnant of the Sagittarius dwarf. There are still enormous trails of stars associated with it. There is still enough structure left for astronomers to compare observations with computer models and ask what kind of orbit produced what we see. In a sense, Sagittarius gives us a chance to watch one of the processes that helped build the Milky Way while it's still underway. Of course, watch is doing a lot of work there. If you sat outside with a blanket and stared at Sagittarius for the rest of your life, you would not see the dwarf galaxy stretch into a ribbon before your eyes. Galactic interactions are patient. Human civilizations can rise, invent clocks, argue about clocks, build space telescopes, and still occupy only a tiny instant compared with the timescale of a galactic orbit. We infer the motion from precise measurements of where stars are, how far away they are, what direction they are moving, how fast they are travelling, and what their light tells us about their composition. That is one reason the Sagittarius stream is so interesting. A stream of stars is not only evidence that something was disrupted, it is also a record of the gravitational environment through which those stars have moved. Once a star is stripped from a dwarf galaxy, it does not simply stop obeying gravity and wander off to begin a quiet, independent life. It continues orbiting within the Milky Way. Stars pulled away at different times spread along related paths, forming long leading and trailing structures around the galaxy. Those paths contain information about the Milky Way itself. If the galaxy's mass were distributed differently, the stream would develop differently. If the dark matter halo around our galaxy has one shape rather than another, the trajectories of stream stars respond to that. If another massive object, such as the Large Magellanic Cloud, perturbs the Milky Way's outer regions, that too can affect the structures astronomers are trying to model. The Sagittarius stream is therefore both debris and evidence. It is the remains of a smaller galaxy, and, at the same time, a tool for studying the large one tearing it apart. This is where the situation becomes slightly unfair to Sagittarius. Imagine losing your stars to a much larger neighbour, and then having astronomers use the resulting mess to measure the neighbour. There is not even a complaints department. The word tearing can also give the wrong mental picture if we imagine something violent in the familiar sense. Galaxies are mostly empty space. Even in crowded stellar regions, the distances between individual stars are enormous compared with the stars themselves. When galaxies interact, direct collisions between stars are not the main story. Gravity is. A galaxy holds itself together because its contents are gravitationally bound. Stars, gas, dark matter, and other components move within the combined gravitational field of the system. Bring a much smaller galaxy into the gravitational field of a much larger one, and the pull is not perfectly equal across the smaller galaxy. The side closer to the Milky Way can experience a different gravitational pull from the side farther away. If those differences become strong enough, stars near the outskirts of the smaller galaxy can be stripped from it. These are tidal forces. The same basic idea appears much closer to home in the tides raised by the moon and sun, although the Sagittarius interaction operates on a completely different scale. and involves the gravitational structure of entire galaxies. The name is useful because it reminds us that the important thing is not simply gravity pulling on an object. It is the difference in gravitational pull across the object. Over repeated passages, those differences matter. A dwarf galaxy that might once have been more substantial can lose material again and again. Stars escape from its gravitational grip. Some end up ahead of the remnant along its orbit. Others trail behind. Given enough time, what began as a compact stellar system can become a long, diffuse set of streams surrounding its host galaxy. Sagittarius has apparently been making this journey for a very long time. Evidence suggests it has passed through the Milky Way's disk multiple times, and researchers using data from missions such as ESA's Gaia have studied how those encounters may have disturbed our own galaxy as well. The relationship is not simply that a large galaxy acts and a small galaxy suffers. Sagittarius is much less massive, but its passages may have produced ripples and helped trigger periods of star formation in the Milky Way's disk. A smaller intruder can still leave a mark. That makes the situation more interesting than a simple story of galactic cannibalism. The Milky Way is stripping Sagittarius, but Sagittarius may also have helped change the Milky Way. In galactic dynamics, even the object losing the encounter can influence the winner. There is something useful in remembering that our own galaxy is not isolated. Astronomy images often show galaxies separated against black backgrounds, each one looking like an individual object with a clean boundary around it. Reality is less tidy. Galaxies have extended halos. They have satellite galaxies. They exchange and strip material. Their gravitational influence reaches far beyond the bright regions we see in photographs. Around the Milky Way, there are faint streams and remnants that record earlier encounters, some discovered only because modern surveys can measure huge numbers of stars accurately enough to notice patterns hidden in the crowd. The Sagittarius Dwarf itself remained unnoticed as a separate galaxy until the 1990s, which may seem surprising. How do you fail to notice an entire galaxy that is relatively nearby? Quite easily, as it turns out, when you live inside another galaxy. Sagittarius lies in a difficult direction, seen through dense regions of Milky Way stars and dust. It is also diffuse. It does not announce itself in the sky as a bright little spiral with a helpful sign saying, "Separate galaxy here." Its stars overlap in our view with stars belonging to the Milky Way, and recognizing that some of them form a distinct system requires careful measurements. Once astronomers identified Sagittarius as a dwarf galaxy, the next surprise was realizing how extensively it had already been disrupted. The stream changed the scale of the story. Sagittarius was not merely a small companion sitting near the Milky Way. Its stars had been spread across an enormous portion of the sky. Researchers began finding parts of the tidal debris at great distances from the surviving core. As surveys improved, the stream became a major target for studying galactic structure. Sometimes a discovery does not simply add one new object to a catalogue, it changes what an existing object means. A faint collection of stars becomes a galaxy. That galaxy turns out to be the surviving core of a much larger disrupted system. Scattered stars become a stream. The stream reveals an orbit. The orbit gives astronomers another way to test the Milky Way's gravitational field. Better measurements have also shown that the Sagittarius stream is not a single, perfectly smooth line. Observations have revealed multiple features, including branches and differences between different portions of the debris. Astronomers compare these structures with simulations that follow how a dwarf galaxy might lose stars during repeated orbits around the Milky Way. If a model places the stream in the wrong part of the sky, gives its stars the wrong velocities, or fails to reproduce major features, something in the model needs attention. Perhaps the assumed orbit is wrong. Perhaps the Milky Way's mass distribution needs adjusting. Perhaps the original Sagittarius dwarf was different from what was assumed. Perhaps another galaxy has been interfering. because apparently even galactic destruction can become a group project. Precise star mapping becomes essential here. ESA's Gaia mission has measured the positions and motions of enormous numbers of stars in the Milky Way. Instead of seeing only where a star appears on the sky, astronomers can combine information about distance, proper motion, radial velocity for many stars, and stellar properties to identify groups moving in related ways. A stream that can be difficult to recognize in an ordinary image can become much clearer when motion is included. Imagine standing in a crowded railway station. If you take one photograph, you see hundreds of people mixed together. It may be difficult to tell who arrived together. Suppose, however, that you could know the direction and speed of every person, where each had come from, and perhaps a few details about what they were carrying. Groups would begin to emerge from the crowd. The Milky Way presents astronomers with a much larger version of that problem. The Sagittarius stars are mixed into our view of the galaxy, but they are not moving randomly. Many retain related motions because of their common origin. By finding those relationships, astronomers can identify debris that would otherwise disappear among the stars of the Milky Way. Unlike passengers in a railway station, these stars can preserve evidence from billions of years of galactic interaction. Some were stripped earlier, others left Sagittarius more recently. Different portions of the stream have travelled through different parts of the Milky Way's halo. Their positions and velocities carry the cumulative effect of gravity along the way. That makes the stream useful for one of the most difficult tasks in astronomy: figuring out how mass is distributed in a galaxy when much of that mass cannot be seen directly. We can see stars, we can detect gas in various ways, but the Milky Way is also embedded in a much larger halo of dark matter, which does not emit light in the ordinary way. Astronomers infer its presence from gravitational effects. The Sagittarius stream gives them a long structure on which those effects have been acting. Instead of examining gravity at only one location, researchers can study stars distributed across a huge orbit around the galaxy. The challenge is that the answer is not simple. Streams respond to the full gravitational environment, and the Milky Way is not a perfectly symmetrical object sitting alone in space. Its disk, central regions, halo, satellite galaxies, and ongoing interactions all matter. The Large Magellanic Cloud, another satellite and a much more massive one than the present-day Sagittarius Dwarf, can influence the motion of the Milky Way and its outer halo. Models that once treated our galaxy as a fixed, quiet gravitational background have therefore had to become more realistic. This is good news for science and slightly inconvenient news for anyone hoping the universe would eventually become easier. It usually does not. Every improvement in observation gives astronomers a clearer view, and clearer views often reveal that the simple version was useful but incomplete. Sagittarius looked like a nearby dwarf galaxy. Then it became a dwarf being disrupted. Its debris showed that the disruption stretched around the Milky Way. The stream became a probe of dark matter and galactic dynamics. Interactions with other satellite galaxies complicated the interpretation further. Meanwhile, Sagittarius continued moving through all of it, entirely unconcerned with how many scientific papers were being written. For us, the important point tonight is much simpler. The Milky Way is not merely a collection of stars rotating quietly in space. It is an active gravitational system with a long history of encounters. Sagittarius gives us a visible example of how a large galaxy can grow while taking apart a smaller one. The process is slow enough that no human will watch it unfold from beginning to end, but clear enough that astronomers can reconstruct what has happened by reading the distribution and motion of the stars left behind. Those stars are the reason we know there is more to Sagittarius than the faint remnant that survives today. They stretch away from their former galaxy, trace its orbit, preserve evidence of repeated encounters, and move through the gravitational field of the Milky Way. By studying them, astronomers learn not only what happened to Sagittarius, but something about the structure and history of our own galaxy. Before following that stream around the sky, though, It helps to look more closely at the object that produced it while there is still a recognisable object left to study. Where was this hidden nearby galaxy? Why did it remain unseen for so long? What kind of system did astronomers finally discover? And what revealed that it was already being torn apart by gravity? That surviving object is the Sagittarius Dwarf Spheroidal Galaxy, and before following the stars that have been pulled away from it, it is worth spending some time with what is still there. Sagittarius is easy to describe as a small companion of the Milky Way, but that description hides almost everything interesting about it. It is nearby by galactic standards, difficult to see, heavily distorted, filled with stars from different periods of its history, and positioned in one of the worst possible places for anyone on Earth trying to notice that it exists. For most of the 20th century, astronomers did not know it was there. This was not because Sagittarius was sitting at some enormous distance near the edge of the observable universe. When it was identified in 1994, estimates placed it roughly 24 kiloparsecs, or around 78,000 light-years, from the Sun, and about 16 kiloparsecs from the centre of the Milky Way. At the time, it was recognised as the nearest known external galaxy. The surprising part was that astronomers had been looking through its region of the sky for generations without recognising the galaxy hiding there. The problem becomes easier to understand when you remember where we are observing from. Earth is not hovering conveniently above the Milky Way with a clear view of everything around it. We are inside the galactic disk. When we look toward the constellation Sagittarius, we're also looking toward the crowded central regions of our own galaxy. There are enormous numbers of Milky Way stars in that direction, along with clouds of interstellar dust that block and redden visible light. Behind that foreground sits the Sagittarius Dwarf, spread thinly across a large area rather than concentrated into an obvious bright object. So, from Earth, Sagittarius does not resemble the classic photograph of a galaxy. There are no easily visible spiral arms. There is no bright oval sitting alone against an empty black background. You look toward it, and mostly see the Milky Way. This is one of those astronomical situations where being close actually makes something more difficult to recognise. A distant galaxy can fit neatly inside a telescope image. Sagittarius is so close and so extended that its stars are spread across a considerable portion of the sky. Its light does not arrive as one compact patch. The galaxy is mixed into the foreground, and the foreground happens to be one of the busiest stellar neighbourhoods available. NASA later summarised the difficulty rather neatly. Sagittarius had gone unnoticed because it was faint, spread across the sky, and hidden behind large numbers of Milky Way stars. That combination allowed an entire galaxy to remain unidentified until 1994, which is comforting news for anyone who has ever spent 10 minutes looking for something that was sitting directly in front of them. Its discovery began during observations that were not originally designed to find a new galaxy. Rodrigo Ibata, Jerry Gilmore and Michael Irwin were studying stars toward the central regions of the Milky Way. Astronomers can learn a great deal by measuring stellar spectra, because a spectrum tells you more than the colour of a star. Features in the spectrum can reveal chemical composition and motion. In particular, shifts in spectral lines allow astronomers to estimate radial velocity, meaning how quickly a star is moving toward or away from us, along our line of sight. When the researchers examined stars in the direction of Sagittarius, they found a large group behaving in a way that did not fit the surrounding Milky Way population. These stars shared similar motions. That was important. A random collection of foreground stars can overlap on the sky by coincidence. From Earth, two stars may appear almost beside one another, while actually sitting thousands of light-years apart and moving in completely unrelated directions. But when many stars in the same region share a distinct pattern of motion, the chance that they belong to one physical system becomes much stronger. Ibata, Gilmore and Irwin concluded that they had detected a large extended group of stars moving together on the far side of the galactic centre. Their 1994 Nature paper interpreted the population as a dwarf galaxy and proposed the name Sagittarius Dwarf Galaxy, after the constellation in which it appeared. They also noted something immediately worrying for the newly recognised system. It was elongated in a direction connected with the Milky Way, suggesting that tidal disruption was already affecting it. Astronomers had effectively discovered a galaxy and evidence of its destruction at almost the same time. To understand what kind of object they had found, the useful word is dwarf. A dwarf galaxy is not simply a normal large galaxy viewed from farther away. It is a genuinely smaller galactic system containing far fewer stars and much less visible material than a galaxy such as the Milky Way. The Milky Way has a large disk, spiral structure, extensive gas and dust, ongoing star formation, a central bulge, and an enormous dark matter halo. A dwarf spheroidal galaxy is far less elaborate in visible appearance. Dwarf spheroidals generally have low surface brightness. Their stars are spread thinly enough that they can be remarkably difficult to notice, even when the galaxy itself is comparatively nearby. They tend to contain older stellar populations and little of the cold gas needed for vigorous present-day star formation. They do not display the grand spiral arms that make large disk galaxies so photogenic. The term spheroidal suggests a roughly rounded stellar system, although Sagittarius has spent enough time under the influence of the Milky Way that expecting a tidy shape would be optimistic. The original observations showed it to be strongly elongated. Later work mapped Sagittarius across an even greater area. What astronomers were looking at was not a small, undisturbed ball of stars orbiting peacefully around the Milky Way. Its shape had already been altered by tidal forces, and the stars still bound to the central body represented only part of a larger structure. There was another clue inside the stellar population itself. Sagittarius did not appear to contain stars that all formed at the same time with the same chemical composition. Early follow-up observations found evidence for a substantial intermediate-age population, a range of metallicities, carbon stars, and different features in its colour magnitude diagrams. In other words, Sagittarius had experienced a more complicated history of star formation and chemical enrichment than you might expect from a simple collection of ancient stars. Metallicity, despite the name, does not mean that astronomers are checking whether stars contain large quantities of iron furniture. In astronomy, elements heavier than hydrogen and helium are generally grouped under the broad label of metals. A star's metallicity provides information about the material from which it formed. The earliest generations of stars formed when the universe contained mostly hydrogen and helium. As stars lived and died, nuclear reactions produced heavier elements and returned some of them to surrounding space. Later generations of stars could then form from material enriched by previous generations. A galaxy containing stellar populations with different metallicities is therefore carrying evidence of its own history. Some stars formed earlier. Others formed from material that had already been chemically enriched. By studying those populations, astronomers can try to reconstruct when star formation occurred and how the galaxy evolved before the Milky Way began removing so much of it. Research on Sagittarius found that its star formation was not limited to one ancient event. One study of its stellar content concluded that star formation had been especially significant roughly 8 to 10 billion years ago, followed by a decline and much lower levels continuing until far more recently in galactic terms. The exact reconstruction depends on which populations and regions are examined, but the important point is that Sagittarius had enough time to develop a genuine internal history before disruption transformed it into the system we see now. That matters because it is easy to think of Sagittarius only as debris. It was not born as a stream. It began as a galaxy capable of holding stars gravitationally, forming multiple stellar populations and, at least for part of its life, evolving as its own system. Long before astronomers on Earth gave it a name, Sagittarius had already existed for billions of years. How massive it originally was is harder to determine because the Milky Way has removed so much material. Imagine trying to estimate the original size of a loaf after someone has been tearing pieces off it repeatedly for several billion years. You can examine what remains. You can count crumbs. You can study where those crumbs landed. You can model the size of each missing piece. But there is no untouched loaf available for comparison. Astronomers face something similar with Sagittarius, except the crumbs are stars and dark matter, and nobody can agree to leave the kitchen alone for long enough to simplify the calculation. The mass Sagittarius possesses today is not necessarily a good guide to the mass it had before its interaction with the Milky Way became severe. Computer simulations of the Sagittarius system often begin with a much more massive progenitor, and then calculate how repeated passages through the Milky Way could strip away stars and dark matter. Different assumptions about its initial mass, orbit, and internal structure can produce different versions of the stream we observe today. Dark matter becomes particularly important. Like other dwarf spheroidal galaxies, Sagittarius is thought to have formed inside a dark matter halo. Dark matter does not emit or reflect enough light for us to see it directly, but its gravity influences the motion of stars. In an intact dwarf galaxy, that invisible mass can provide much of the gravitational structure holding the stellar component together. Sagittarius complicates the picture because its dark matter would also have been vulnerable to tidal stripping. In many models, the extended dark matter halo begins losing material before the more centrally concentrated stars are removed in large numbers. By the time a dwarf galaxy is visibly stretched into streams of stars, much of its original dark matter halo may already have been stripped away. That makes the surviving central region something of a reduced version of the original galaxy. One particularly conspicuous object associated with Sagittarius is Messier 54, a dense globular cluster located in the Sagittarius system. Charles Messier discovered M54 in 1778, more than 2 centuries before anyone realized that Sagittarius itself was a separate galaxy. Messier was compiling his famous catalogue partly because fuzzy objects in the sky could be confused with comets, and M54 became one of those catalogue entries. For generations, it was naturally treated as a globular cluster belonging to the Milky Way. Then Sagittarius was discovered around it. M54 is now recognized as belonging to the Sagittarius Dwarf system, and NASA describes it as the first globular cluster found outside the Milky Way, although nobody knew that when it was originally observed. It lies roughly 90,000 light-years from Earth, according to NASA's current Messier catalogue description. There is something wonderfully inconvenient about that sequence of events. Astronomers discovered the cluster in the 18th century. They discovered the galaxy associated with it in the 20th. For more than 200 years, humanity had catalogued one of the galaxy's most prominent objects without realizing that the larger system was there. M54 is extremely dense compared with the diffuse stars around it, so it is much easier to detect. A globular cluster packs large numbers of stars into a relatively compact region. Sagittarius itself spreads its stars over a much larger area with a very low surface brightness. The small object announces itself. The galaxy containing it blends into the background. Other globular clusters have also been connected with Sagittarius. Early studies proposed associations with clusters including ARP2, Terzan 7, and Terzan 8, helping astronomers build a picture of a dwarf galaxy that brought its own cluster system into the Milky Way's neighbourhood. This provides a useful reminder of what happens during galactic mergers. The Milky Way does not simply swallow a smaller galaxy as one object. It acquires pieces. Stars that formed inside Sagittarius can become part of the Milky Way's halo. Star clusters associated with the dwarf can eventually orbit the larger galaxy. Dark matter from the original system can be redistributed. Material stripped during different passages ends up in different places. Given enough time, the original identity of the smaller galaxy becomes increasingly difficult to recover. A star does not carry a label saying, "Former property of Sagittarius." Astronomers have to work that out. They use motion, they use chemical abundance patterns, they use ages, They examine how stars are distributed through space. If many stars share the right combination of characteristics, researchers can connect them to a common origin, even when they are now separated by enormous distances. Sagittarius is particularly valuable because we have both sides of that process available at once. There is still a recognizable remnant galaxy. There is also debris outside it. That means researchers can compare stars still associated with the central body to stars that have been stripped away. Their chemical compositions can help establish relationships. Their motions can reveal when and how they became separated. Different sections of the debris may represent material removed during different encounters with the Milky Way. The galaxy gives us the source and the trail. Its present shape also tells us something immediate about the strength of the interaction. A small satellite orbiting far from a larger galaxy can remain relatively stable if its own gravity is sufficient to hold it together. Move that satellite closer, and the gravitational difference across it grows stronger. The side nearer the Milky Way feels a different pull from the side farther away. At some point, stars in the outer parts of Sagittarius can no longer remain securely bound to the dwarf. The process does not remove every star at once. The central regions are more tightly bound, so they survive longer. Material farther out is easier to strip. Repeated passages gradually reduce the satellite, while the remnant continues moving along its orbit. This is one reason early researchers faced a puzzle. Sagittarius was clearly close to the Milky Way and visibly distorted, yet it still existed. Models had to explain how a dwarf galaxy could survive repeated encounters without being destroyed much earlier. Work in the 1990s explored whether the distribution of dark matter within Sagittarius could help explain its persistence, even while tidal forces were steadily reshaping it. Survival does not mean comfort. The dwarf can remain recognizable while losing enormous amounts of material. Think of a snowball rolling through warm water, except it has been doing so for billions of years. Gravity replaces melting, and the bits that come off continue orbiting the same galaxy, rather than collecting sadly around a drain. What remains in Sagittarius today is therefore the dense survivor of a much larger history. Its elongated structure, its unusual position, its shared stellar motions, its globular clusters, its mixture of stellar populations, and its relationship with the Milky Way all tell pieces of the same story. This is not a galaxy approaching the Milky Way for the first time in pristine condition. It is a system that has already been altered by repeated interaction. ESA studies using Gaia data have described Sagittarius as having orbited the Milky Way for billions of years, with repeated passages through the galactic disk. One 2020 analysis identified 3 major interactions connected with episodes of enhanced star formation in the Milky Way, illustrating that the little dwarf has not simply been passively losing stars. Its orbit has allowed it to disturb the much larger galaxy as well. The scale difference is enormous. ESA described the Milky Way as roughly 10,000 times more massive in the context of those interactions. Yet the passages of Sagittarius were still capable of producing measurable effects in the disk. A small galaxy does not need to overpower the Milky Way to disturb it. It only needs enough mass, enough speed, and the right orbit. Drop a pebble into a pond and the pebble does not defeat the pond. It still makes ripples. Sagittarius has been making very large ripples. At the same time, every close encounter changes Sagittarius more severely than it changes the Milky Way. The larger galaxy has an enormous gravitational advantage. Each pass can remove more material and alter the dwarf's orbit. Over long periods, the central remnant becomes smaller, while its lost stars occupy increasingly large regions around the Milky Way. From Earth, this means the object identified in 1994 is only the obvious surviving concentration. The rest of Sagittarius is no longer located entirely in Sagittarius. Its former stars extend far beyond the boundaries astronomers first mapped around the dwarf. Some are distributed across huge arcs of the sky. They are separated from the main body by tens of thousands of light years, yet their motions and properties reveal that they once belonged to the same galaxy. The realization that those distant stars were related to Sagittarius changed the entire picture. Instead of seeing one elongated dwarf galaxy near the galactic center, astronomers began to recognize something much larger. Long concentrations of stars tracing the path of the dwarf around the Milky Way. The odd shape noticed at discovery was not simply a damaged edge. It was part of an ongoing process that had already scattered Sagittarius across our galactic surroundings. Finding those scattered stars was not straightforward. They had to be picked out from the Milky Way population, just as the original dwarf had been. Astronomers needed large surveys, reliable distance indicators, stellar motions, and distinctive populations that could be followed across the sky. Those stars that seemed to belong to no galaxy at all became some of the most useful clues Sagittarius could have left behind. Once astronomers understood that the dwarf was being disturbed by the Milky Way, an obvious question followed. If stars were being removed from Sagittarius, where were they going? The simple answer was that they should not disappear. They should continue moving through the Milky Way's gravitational field on paths related to the orbit of the galaxy they came from. This possibility had been discussed almost immediately after Sagittarius was discovered. In 1995, researchers using computer simulations explored what repeated encounters with the Milky Way might do to the newly identified dwarf. The model suggested that stars stripped from Sagittarius should remain detectable as moving groups in the galactic halo. Instead of staying concentrated around the surviving dwarf, they would spread along its orbit and preserve a recognizable relationship in their positions and motions. That gave observers something useful to search for. They did not necessarily need to find another obvious concentration of stars. They needed to find stars that behaved as though they had once traveled together. This is an important distinction because a tidal stream is easy to misunderstand when you first hear the term. It sounds as though there should be a bright river running through the sky, something you could point a telescope toward and immediately recognize. In reality, the stars can be extremely sparse. They may cover tens or hundreds of degrees across the sky, while remaining buried among much larger numbers of ordinary Milky Way stars. The stream is obvious only after you know what information to compare. One of the first strong observational hints came surprisingly close to the known body of Sagittarius. In the mid-1990s, astronomers found stars associated with the dwarf roughly 10 degrees away from its center, farther out than the previously recognized boundary of the galaxy. Among them were RR Lyrae stars, red horizontal branch stars, and main sequence stars whose properties matched the distance and stellar population of Sagittarius. 10 degrees may not sound very impressive. On a map of Earth, it is simply a bit of angular separation. On the sky, though, 10 degrees is substantial. The full moon is only about half a degree across. Put 20 full moons side by side, and you begin to get an idea of the angular distance involved. The important point was not the visual size. It was that Sagittarius stars were turning up well beyond the region where astronomers had expected the galaxy to end. Perhaps the dwarf was simply larger than first believed. That was possible. But another explanation was becoming difficult to avoid. Some of those outer stars might no longer be gravitationally bound to Sagittarius at all. They could be debris. Astronomers had already noticed that the dwarf was elongated. Its shape was suspicious for a satellite living so close to the Milky Way. Finding related stars farther away strengthened the idea that the larger galaxy was stripping material from it. A bound galaxy usually becomes less dense as you move outward from its center. Eventually, the number of stars associated with the system should fall away, but a galaxy undergoing tidal disruption can show an additional population beyond the region expected for a stable object. Those stars may still sit close to the dwarf on the sky while already being dynamically detached from it. They have left home without going very far yet. This made the outskirts of Sagittarius particularly interesting. A star a few degrees from the center might look like a distant member of the dwarf, an escaping star, or a Milky Way star that happens to lie in the same direction. Sorting those possibilities required more observations. Distance helped. Stellar populations helped. Velocity helped even more. If stars spread across a region of the sky share distances and motions consistent with Sagittarius, then the case for a physical connection becomes stronger. One strange star can be a coincidence. Hundreds of stars following a coordinated pattern are much less cooperative with that explanation. Researchers also looked at the way the velocity of Sagittarius stars changed across the dwarf. A coherent velocity gradient could reveal how the system was moving and whether material around it was beginning to separate from the main body. By the late 1990s, observations and dynamical models were increasingly supporting a picture in which unbound stars surrounded Sagittarius and extended away from it. Then astronomers began finding possible pieces much farther out. This was where the scale of the problem changed. A tidal tail extending 10 degrees from a dwarf galaxy is interesting. A population of related stars found 50 or 60 degrees away begins to suggest that the original galaxy has been distributing itself across a very large fraction of the sky. Carbon stars provided one early route into this larger structure. Carbon stars are evolved stars whose atmospheres contain enough carbon to give them distinctive spectral characteristics. Certain types are luminous enough to be detected at large distances, which makes them useful traces of distant stellar populations. Surveys of faint carbon stars in the galactic halo found an unusual pattern. Some were distributed along a path consistent with the expected orbit of Sagittarius. This did not mean that every carbon star in the halo came from the dwarf. Astronomy would be much easier if stars agreed to organize themselves that neatly. The useful part was the overdensity and alignment. A population appeared where models suggested stripped Sagittarius debris might be found. The stars were providing the first hints that the tidal material could extend far beyond the obvious central galaxy. Around the same period, theoretical work was making an even more ambitious prediction. If Sagittarius had been losing stars during repeated orbits, its debris might extend around a large fraction of the Milky Way. Stars stripped at different times would occupy different positions along the dwarf's orbital path. Material removed relatively recently would remain closer to Sagittarius. Older debris would have had more time to spread. The result could be an enormous stream wrapping around the galaxy. That sounds straightforward in a diagram. You draw the Milky Way in the middle, sketch a long curved line around it, label the line Sagittarius Stream, and the entire situation appears to have been solved before lunch. Observing it from Earth is less considerate. We are inside the Milky Way. The Sagittarius orbit is seen from our moving position within the galactic disk. Different parts of the stream lie at different distances. Some pass through crowded regions of the sky. Some contain stellar populations that are easier to detect than others. Several unrelated structures also exist in the galactic halo, so finding an overdensity of stars does not automatically make it part of Sagittarius. Astronomers needed ways to separate a real stream from the general clutter. One technique uses a colour magnitude diagram. This is one of the basic tools of stellar astronomy. Instead of plotting stars according to where they appear in the sky, astronomers plot their brightness against their colour. Because stellar brightness and colour depend on properties such as mass, age, composition, and stage of evolution, a population of related stars can form recognisable patterns on the diagram. A star cluster, for example, produces characteristic sequences because its stars are approximately the same distance away and formed from related material. A dwarf galaxy is more complicated, but its stellar populations still create features that can be compared from one field to another. So suppose you look at a patch of apparently ordinary galactic halo far from Sagittarius. There is no obvious dwarf galaxy there. Nothing announces itself in a normal telescope image. But when the stars are plotted by colour and brightness, an additional sequence appears. Its position indicates that a population of stars is sitting at a similar distance. Better still, the sequence resembles stars already known in Sagittarius. Now the empty-looking patch becomes suspicious. This approach helped astronomers identify distant concentrations that could belong to the Sagittarius debris. Around 2000 and 2001, observations reported low-density stellar structures many tens of degrees from the dwarf. Some detections were roughly 60 degrees away from its centre and were consistent with models predicting a northern stream. 60 degrees is 1/6 of the way around the entire sky. At that point, Sagittarius was no longer behaving like a dwarf galaxy with a slightly untidy edge. The Milky Way appeared to be stretching it across enormous distances. The Sloan Digital Sky Survey then gave researchers a much larger set of stars to work with. SDSS was designed to map large areas of the sky with consistent measurements. Instead of examining a few carefully chosen fields, astronomers could compare millions of stars across broad regions. That is exactly the kind of survey needed for structures that are individually faint but collectively enormous. In early SDSS observations, researchers found large stellar overdensities in the galactic halo. Some were located far from the known centre of Sagittarius, but had colour and brightness distributions consistent with Sagittarius populations. One reported structure covered more than 100 square degrees and lay roughly 75 degrees from the dwarf's centre. Imagine discovering that pieces of an object are scattered 75 degrees away from the object itself. At human scale, that would be less like finding crumbs beside a loaf, and more like finding the rest of breakfast in another county. The growing number of detections began to connect. A stellar population here, another farther north, carbon stars following a similar route, velocity measurements matching what tidal models expected, distance estimates tracing a large orbit. Each result on its own could contain uncertainty, but together they were forming a coherent picture. The dwarf was surrounded by much more than a short tail. It had produced a stellar stream. There are actually two basic directions in which material can spread when a satellite is tidally disrupted. Some stars move into what astronomers call the leading arm. Others enter the trailing arm. The distinction comes from where the stripped stars move relative to the surviving satellite along its orbit. Stars leaving through the side close to the Milky Way can end up on slightly different orbits with shorter periods, allowing them to move ahead of the dwarf. These become part of the leading debris. Stars escaping from the opposite side can occupy slightly larger orbits with longer periods and fall behind, becoming trailing debris. Nobody has to push them forward or backward. The difference develops naturally from their orbital energy and the gravitational conditions under which they escape. The dwarf continues along its own path while the released stars slowly separate from it. Over one orbit, the tails grow. After repeated orbits, older material can wrap farther around the Milky Way. This is why a tidal stream should not be imagined as smoke blown behind a moving object. Smoke simply trails because the source moves through an atmosphere. A stellar stream develops because stars released from a satellite move onto nearby but slightly different galactic orbits. Some get ahead. Some fall behind. All of them continue responding to the Milky Way's gravity. By the beginning of the 2000s, the leading and trailing structures of Sagittarius were appearing over larger and larger areas, but another survey made the geometry much clearer. The 2-micron all-sky survey, better known as 2MASS, observed the sky in near-infrared light. Near-infrared observations offered an important advantage for Sagittarius, because infrared wavelengths can penetrate interstellar dust more effectively than visible light. That is useful when your target has chosen to hide behind some of the most inconvenient dust in the Milky Way. 2MASS also provided astronomers with a particular population of stars that worked extremely well as tracers, M-giants. M-giant stars are luminous, cool, evolved stars. Sagittarius contains a prominent population of them, and their infrared colours help distinguish suitable candidates across the sky. Because they are intrinsically bright, they can be detected over the large distances involved in the Sagittarius system. Instead of trying to identify every star Sagittarius had ever lost, researchers could follow a recognisable subset. The result was one of the clearest early maps of the disruption. Using M-giants from the completed 2MASS survey, astronomers mapped the core and tidal arms of Sagittarius across the sky. A striking trailing tail extended for more than 150 degrees from the centre of the dwarf across the southern galactic hemisphere. A leading arm extended north of the galactic plane, travelled outward to large galactic distances, curved across the northern sky, and began descending again. The stream was becoming an all-sky structure. That phrase can sound slightly misleading. It does not mean Sagittarius stars cover every square degree of sky equally. They trace long, broad paths associated with the dwarf's orbit. Seen from our location, those paths can cross vast portions of the celestial sphere. The remaining dwarf is simply the densest surviving portion of something much larger. Velocity measurements provided another test. If the M giant selected from two mass truly belong to one tidal stream, their radial velocities should not be random. Their speeds toward or away from us should change systematically as we move along the stream because we are observing different parts of one large orbital structure. Spectroscopic observations showed exactly that kind of trend in the trailing arm. Stars selected along the suspected debris shared a relatively narrow range of motions around the expected pattern. Astronomers sometimes describe such a stream as dynamically cold, meaning that the stars have a comparatively small velocity dispersion around their common motion. Cold does not mean the stars have low surface temperatures. An M giant is still doing perfectly well in the temperature department. It means the population is dynamically ordered. That order is extremely useful. Imagine releasing a group of runners onto a huge track. After some time, they spread out because some move slightly faster than others. If you encounter them much later, they may be separated by kilometers, but their direction and speed still reveal that they belong to the same race. Tidal debris works under much more complicated gravitational conditions, but the principle is similar. Stars that once belonged to Sagittarius can become widely separated while preserving a relationship in orbital motion. The stream, therefore, gave astronomers more than proof of destruction. It gave them a record of when material had been removed. Recently stripped stars tend to occupy different portions of the stream from stars lost during earlier passages. Chemical composition can also change along the debris, because different parts of the original dwarf may have contained different stellar populations. If Sagittarius had gradients in age or metallicity before disruption, the Milky Way did not necessarily strip every population equally at every encounter. The stream could preserve layers of the dwarf's history. That made each new detection more valuable. A star far from Sagittarius was not simply a lost member. Its location could provide information about the dwarf's orbit. Its velocity could test models of the Milky Way's gravitational field. Its chemistry could link it to the Sagittarius population. Its distance could help reconstruct the three-dimensional shape of the stream. A large sample could reveal where one wrap of debris crossed another. The Milky Way had turned Sagittarius into a very untidy experiment and then distributed the results across the sky. There was also a larger reason astronomers cared so much about these first streams. Modern models of galaxy formation predict that large galaxies grow partly by absorbing smaller systems. If that is true, the outer Milky Way should contain remnants of past accretion events. Some satellites may survive, others may be partly disrupted. Some could have been destroyed so thoroughly that only streams of stars remain. Sagittarius provided a nearby example of the process in action. Before its discovery, the idea that the Milky Way's halo contained debris from smaller galaxies was already part of galaxy formation theory. Sagittarius gave astronomers a system where the parent satellite could still be identified and the debris could be followed outward from it. You could compare the surviving galaxy with the stars it had already lost. That connection was crucial. Without Sagittarius itself, a stream is a clue without an obvious culprit. With the dwarf still present, the entire process can be studied from the source outward. Researchers could ask how a stream grows, how quickly it spreads, how long coherent structures survive, and what happens to the satellite after repeated stripping. Those lessons could then be applied to older streams whose original galaxies may already be gone. This is one reason the galactic halo began to look less smooth as surveys improved. Earlier descriptions often treated the halo as a broad, diffuse population of old stars surrounding the disk. That remains useful at large scales, but increasingly detailed surveys revealed clumps, streams, shells, and other structures inside it. Some stars that seemed to be ordinary members of the Milky Way halo were actually immigrants from smaller systems. The halo had memory. Not memory in any mysterious sense. Its stars simply retain measurable consequences of where they came from. Orbits persist. Chemical abundance patterns persist. Groups can remain identifiable long after the original galaxy begins to dissolve. The Sagittarius stream became one of the largest and best-studied examples of that principle. It also forced astronomers to change how they thought about the dwarf itself. When Sagittarius was first identified, the object of interest was the concentration of stars near its core. Once the debris was mapped, that core became only the surviving centre of a system extending far beyond it. The visible dwarf had not merely grown a pair of tails. Much of the original galaxy had become the tails. Stars once orbiting inside Sagittarius now travel around the Milky Way. Some are tens of thousands of light-years from the remnant. Some occupy the leading arm. Others belong to the trailing arm. Older wraps can overlap newer ones when viewed from Earth, creating a three-dimensional structure far more complicated than a single curved line. And the process continues. Sagittarius is still moving. Its remnant is still gravitationally bound enough to remain recognizable. The Milky Way is still exerting tidal forces across it. Future passages will continue altering whatever survives. The first distant stars therefore revealed something that could not be understood simply by studying the dwarf's central region. Why are stars pulled away from Sagittarius into two enormous streams? Why do these tidal arms grow longer with each orbit? And how can the dwarf galaxy be stretched apart without its individual stars colliding with those of the Milky Way? The Milky Way does not need to touch Sagittarius to dismantle it. Gravity is enough, provided that gravity pulls on one side of the smaller galaxy differently from the other, and that difference becomes especially important each time Sagittarius moves through the regions where the Milky Way's gravitational field is strongest. That difference in gravity is the key to almost everything we have seen so far. Sagittarius is not being dismantled because the Milky Way reaches out and pulls every one of its stars in the same direction with the same strength. If that happened, the entire dwarf galaxy would simply accelerate together. Its stars would remain bound to one another while the whole system changed its motion. The damage comes from the fact that gravity is uneven. Every part of Sagittarius feels the Milky Way's gravitational pull, but not every part feels exactly the same pull. The side of the dwarf that happens to be closer to the Milky Way experiences a slightly stronger gravitational attraction than the side farther away. Across a human-sized object, a difference like this would be far too small to matter. Across a galaxy stretching for thousands of light-years, it can become extremely important. That uneven gravitational pull is what astronomers call a tidal force. The word may sound familiar because the same basic effect operates on Earth. The Moon pulls gravitationally on the entire Earth. The side of Earth facing the Moon is slightly closer to it, and therefore experiences a stronger lunar pull than Earth's centre. The far side is slightly farther away, and experiences a weaker pull. Those differences contribute to the ocean tides. There are many extra details involved in Earth's tides, including the rotation of the Earth-Moon system and the shapes of ocean basins. But the underlying gravitational idea is the useful part here. Gravity varies with distance. Now replace Earth with a dwarf galaxy. Replace the Moon with the Milky Way. Increase the scale until the object being stretched contains millions or billions of stars. The basic principle survives. Sagittarius has its own gravity. That gravity tries to keep its stars bound to the dwarf. A star near the centre is surrounded by much of the galaxy's mass and is relatively difficult to remove. A star far out in the dwarf's outskirts is held less securely. If the Milky Way's tidal influence becomes strong enough, the balance changes. There is a region around a satellite galaxy within which the satellite's gravity can effectively retain material against the tidal influence of the larger galaxy. Astronomers often describe this in terms of a tidal radius. The exact calculation depends on the orbit and the mass distributions involved, so there is no single permanent boundary drawn around Sagittarius. But the concept is straightforward. Deep inside that region, a star can remain bound to the dwarf. Far enough outside it, the Milky Way's gravitational influence dominates the star's long-term motion. As Sagittarius moves closer to the Milky Way, the tidal influence grows stronger, and that safe region can effectively shrink. Stars that had previously been securely attached to the dwarf can suddenly find themselves near or beyond the region where Sagittarius can hold on to them. The star does not receive a notification. There is no moment when it changes category from Sagittarius star to Milky Way stream star. Its orbit simply changes. For a while, a newly stripped star may remain close to Sagittarius. It may move beside the dwarf closely enough that an observer could still mistake it for an ordinary outer member of the galaxy. Over time, however, small differences in orbital motion cause the star to drift away. This is how an object can lose stars continuously, without anything resembling an explosion. The Milky Way simply changes who those stars are orbiting. ESA has described the tidal influence on Milky Way satellites in very direct terms. As a dwarf orbits the galaxy, the Milky Way's gravitational pull tries to wrench it apart. A sufficiently massive dark matter component can help a dwarf resist that disruption, but repeated close passages can still remove material. Sagittarius has been exposed to this process repeatedly. Its orbit has carried it through the Milky Way's environment for billions of years, and evidence indicates that it has crossed the galactic disk multiple times. Research using Gaia data has linked major passages of Sagittarius with disturbances in the Milky Way disk, while the dwarf itself has progressively lost material during its interaction with the much larger galaxy. It helps to separate two ideas that are sometimes mixed together when people hear the word collision. A galactic collision does not usually mean individual stars smashing into one another. Galaxies are huge, but stars are tiny compared with the distances between them. Two galaxies can pass through one another, while the overwhelming majority of their stars never come close to a direct stellar impact. The gravitational fields of the galaxies, however, affect everything. Stars change orbits. Gas can be compressed or displaced. Disks can be disturbed. Satellite galaxies can lose stars. Dark matter responds gravitationally as well, so Sagittarius can pass through regions occupied by the Milky Way without its stars behaving like cars meeting at an intersection. The real collision is gravitational. That is slower, less obvious, and much more effective at rearranging an entire galaxy. Picture Sagittarius approaching the inner part of its orbit around the Milky Way. As it moves inward, the gravitational field becomes stronger. More importantly, the difference in that field across the dwarf becomes larger. The Milky Way pulls on the near side slightly more strongly than it pulls on the centre. It pulls on the far side slightly less strongly than it pulls on the centre. Relative to Sagittarius itself, those differences create stretching along the direction toward and away from the Milky Way. At the same time, other components of the tidal field can compress the system in perpendicular directions. The overall effect is not simply that the dwarf becomes longer like a piece of chewing gum pulled from both ends, although that is not a terrible starting image. The stars are moving on orbits. Sagittarius is rotating around the Milky Way. Its own gravity is changing as it loses mass. The Milky Way is not a perfect sphere. Other massive satellites can affect the motion. Everything is moving while the stretching occurs. This is why astronomers rely heavily on numerical simulations. Give a computer model a dwarf galaxy containing many simulated particles. Place it inside a model of the Milky Way's gravitational field. Give the dwarf an orbit. Allow the system to evolve. Stars near the centre mostly remain with the dwarf. Particles farther out begin to escape. After enough time, two extended structures develop. One runs ahead of Sagittarius along its orbit, the other falls behind it. These are the leading and trailing tidal arms. The reason there are two of them becomes clearer if we follow individual stars. Consider a star sitting on the side of Sagittarius nearer the Milky Way when it becomes unbound. Because it escapes from the inward side, it can move onto an orbit around the Milky Way, with somewhat different energy and angular momentum from the orbit of the Sagittarius remnant. In a simplified picture, material stripped inward can settle onto a smaller orbit around the Milky Way. Objects on smaller galactic orbits generally complete their journeys more quickly. That star gradually moves ahead of Sagittarius. It joins the leading tail. Now consider a star escaping from the side farther from the Milky Way. It can move onto a slightly larger orbit. Its trip around the galaxy takes longer. Sagittarius begins pulling ahead. That star becomes part of the trailing tail. Nothing literally pushes one group forward and the other backward. They're all moving in the same broad orbital system. The difference comes from how their new orbits compare with the orbit of the dwarf they left. This also explains why the tails grow gradually. Immediately after a star escapes, the difference in orbital period may be small. The star can remain near Sagittarius for a while. Complete another section of the orbit, and the separation increases. Give the system hundreds of millions of years, and stars removed during the same general encounter can spread across an enormous arc. Repeat the process on several passages, and Sagittarius leaves behind multiple generations of debris. The resulting structure is less like a single ribbon produced in one event, and more like overlapping material peeled away at different times. That distinction becomes important when astronomers try to reconstruct the history of the stream. Stars stripped during the dwarf's most recent close passage are dynamically young debris. Material lost one orbit earlier has had more time to separate. Still older debris may have travelled far enough around the Milky Way that it overlaps other sections of the stream when viewed from Earth. A map of the Sagittarius stream can therefore contain several moments from the dwarf's history at once. We happen to see all of them now because light from those stars reaches us from different locations. This gives astronomers a remarkably useful form of archaeological evidence. Suppose you know where the Sagittarius remnant is today. You measure its motion. Then you identify stars along the leading arm and trailing arm. You measure their distances and velocities. Now you can ask which simulated history produces a stream that looks like the real one. If the simulated leading arm goes too far north, something is wrong. If the trailing material is moving at the wrong velocity, something is wrong. If the distances do not match, something is wrong. The orbit may need changing. The original mass of Sagittarius may need changing. The Milky Way model may need changing. The assumed distribution of dark matter may need changing. The stream becomes a test of the gravitational environment that produced it. This is why the Sagittarius debris has attracted so much attention from researchers studying the Milky Way's mass. A stellar stream is not frozen after it forms. Every star continues to travel through the galactic gravitational field. Its path responds to the distribution of mass it encounters. The disk contributes gravity. The central bulge contributes gravity. The extended dark matter halo contributes gravity. Massive satellite galaxies contribute additional perturbations. A model that accurately reproduces the stream must account for enough of that environment to send the stars to the correct places. One influential numerical model of Sagittarius showed that its observed positions, distances, and velocities could place strong constraints on the Milky Way's gravitational potential. The model reproduced much of the relatively young Sagittarius tidal debris by following the gradual disruption of a progenitor dwarf inside a specified galactic mass distribution. This is an elegant idea, but it does not mean Sagittarius has provided one simple answer for the exact shape of the Milky Way's dark matter halo. Quite the opposite. As observations have improved, the stream has revealed additional structure. The leading and trailing arms do not behave like perfectly smooth lines. There are branches. There are differences in stellar populations. There are orbital features that can be influenced by the Large Magellanic Cloud. Modern analyses have found evidence that the LMC's gravitational pull has altered the motion of parts of the Sagittarius stream, including sections of the leading arm and distant trailing debris. The lesson is not that tidal streams failed as gravitational tools, it is that they are sensitive enough to notice more than one source of gravity. That is actually what makes them useful. A long stellar stream can act like a set of test particles distributed around the galaxy. If something massive perturbs their paths, the stream can preserve evidence of that disturbance. It is a very large detector with no electronics. The stars do the measuring simply by moving. The process that creates the stream also changes Sagittarius itself. Every time the dwarf loses mass, its own gravitational grip becomes weaker. Imagine a satellite with a substantial outer halo of dark matter surrounding a more concentrated stellar component. As tides remove the least tightly bound outer material, the satellite becomes less massive. With less mass, it may have a harder time holding onto the material that remains. Later passages can then remove additional layers. The disruption can become progressive. This does not necessarily mean the entire galaxy vanishes during the next encounter. These central regions can remain dense enough to survive for a long time, even after the outskirts are heavily stripped. That is what makes the remnant of Sagittarius so informative. We are seeing a system after substantial damage but before complete dissolution. It has lost enough material to create a stream wrapping around the Milky Way, yet enough remains near its core for us to identify the original source. Go too early in the process and there may be no impressive stream yet. Go too late and the parent dwarf may be gone. Sagittarius has arrived at a useful moment for astronomers, although probably not a useful moment for Sagittarius. Repeated stripping can also sort stars according to where they originally lived inside the dwarf. Suppose Sagittarius once contained a radial metallicity gradient. Stars nearer its centre might on average have had different chemical compositions from stars in the outskirts, because the dwarf's star formation and chemical enrichment history varied with radius. The stars farthest out would generally be easier for the Milky Way to remove. Early stripping could therefore preferentially take one chemical population. Later stripping might reach farther into the original galaxy and remove stars with somewhat different properties. Observations of the Sagittarius debris do show chemical differences between the core and parts of the stream, and studies have used these gradients to infer something about the internal structure of Sagittarius before disruption. Research on the trailing arm, for example, has found a metallicity gradient consistent with tidal stripping. From a progenitor that already possessed an internal chemical gradient. Gravity is therefore not merely stretching the shape of Sagittarius. It is dismantling the galaxy in an order. The loosely bound material tends to leave first. More tightly bound regions last longer. The stream becomes a rough sequence of what was removed and when. This is one reason astronomers care so much about locating debris from different passages. Older sections can preserve information about earlier versions of Sagittarius, when it contained more mass than the remnant we observe today. The farther backward researchers try to reconstruct the interaction. However, the more uncertain the calculation becomes. Sagittarius has been losing mass. Its orbit has evolved. The Milky Way itself has evolved. The Large Magellanic Cloud has altered the gravitational environment. The galactic disk can respond to satellite passages instead of acting as a perfectly rigid background. A realistic simulation has to decide which of these effects matter enough to include. Then it has to reproduce what we actually observe. This is computationally demanding, but the basic physical idea underneath all the complexity remains surprisingly simple. Gravity is stronger at smaller distances. Sagittarius is large enough that different parts of it occupy different distances from the Milky Way. Those differences produce tidal forces. The dwarf's own gravity fights to keep its stars together. The Milky Way's tidal field pulls some of them onto new orbits. The stars spread ahead and behind. Time turns those escaped groups into long arms. Repeated passages make the arms longer and more complicated. Eventually, a galaxy that was once a compact system becomes partly distributed around another galaxy. There is no need for stars to collide. There is no need for a dramatic explosion. The same gravitational law that keeps Earth orbiting the Sun can, under different circumstances, take a galaxy apart. The time scale is what makes it look gentle. If we could compress several billion years into a few minutes, Sagittarius would probably seem much less peaceful. We would watch it circle the Milky Way. Its shape would distort as it approached regions of stronger tidal influence. Streams would peel away. The remnant would shrink. Old debris would continue wrapping around the galactic halo. Later debris would begin tracing similar but not identical paths. The Milky Way disk itself would respond to close encounters. Then the cycle would repeat with a smaller Sagittarius returning again. Viewed at normal speed, almost nothing appears to happen. A star can spend an entire human lifetime moving only an immeasurably small fraction of its full galactic orbit. That difference between human time and galactic time is part of what makes stellar streams so useful. We cannot watch the complete interaction unfold, but we do not need to. Different stars are already sitting at different stages of the process. The remnant shows us what remains bound. Nearby debris shows us material removed more recently. Long arcs farther away preserve older stripping events. The whole stream is the interaction spread across space. Instead of waiting hundreds of millions of years to watch Sagittarius move, astronomers examine where different pieces have already gone. This also helps explain the remarkable width of the stream. The word ribbon is useful, but no real stellar stream is an infinitely thin mathematical curve. Stars inside Sagittarius had their own velocities before they escaped. They didn't all leave from precisely the same location, at precisely the same speed. The dwarf had internal structure. Its orbit changed. The galactic potential is complex. As the stars spread, these small differences produce a stream with measurable width and internal variation. Sagittarius was also far more substantial before the Milky Way stripped so much of it, so the original system was capable of producing broad tidal debris rather than the extremely narrow streams associated with smaller progenitors such as globular clusters. That width contains information too. The physical thickness and velocity dispersion of a stream depend partly on the system that produced it. A very low mass, dynamically cold globular cluster can form a thin stream. A dwarf galaxy with a larger internal velocity dispersion and a substantial dark matter history can produce broader debris. Astronomers can therefore examine the shape of a stream and ask what sort of parent object was required to create it. Sagittarius conveniently leaves the answer nearby in the form of its surviving core. The ribbons are not separate objects that happen to appear around the same time. They are Sagittarius. They are simply Sagittarius after gravity changed the orbits of its stars. That point becomes stranger the longer you think about it. A galaxy is usually defined in our minds as a place. There is the Milky Way over here. Andromeda is over there. A dwarf galaxy occupies some smaller region around a centre. But once tidal disruption becomes severe, that simple picture begins to fail. Where does Sagittarius end? Is it only the stars still gravitationally bound to the core? Do we include the stars stripped during the last orbit? What about those lost several orbits ago and now tens of thousands of light years away? They are no longer members of the dwarf dynamically, yet chemically and historically, they belong to Sagittarius. The galaxy has become partly an object and partly a trail. That is what tidal disruption does. It converts a bound system into orbital structure. And the Sagittarius stream is unusually dramatic because the process has been operating for so long and across such a large orbit. The leading and trailing arms now reach through huge regions of the galactic halo. Their stars occupy different distances from us, follow different portions of the orbit, and record different stripping events. Once those escaped stars are followed far enough from Sagittarius, the scale of the disruption becomes difficult to appreciate from an ordinary map of the night sky. The surviving dwarf occupies one region. The stars that once belonged to it stretch through enormous parts of the Milky Way's halo, appearing above and below the galactic disk at different distances from Earth and in more than one overlapping structure. What began as a search for a damaged satellite galaxy eventually revealed one of the largest coherent stellar streams surrounding the Milky Way. This is the Sagittarius stream. Calling it a river of stars is useful as long as we remember that the river is not flowing through space in the way water moves through a channel. There is no physical tube connecting the stars. There is no current carrying them. There is no riverbank. Each star is following its own orbit through the gravitational field of the Milky Way. They appear to form a stream because those orbits remain related. The stars came from the same dwarf galaxy, were stripped under similar conditions, and continue travelling along paths that preserve that common history. From far outside the Milky Way, if we had the impossible luxury of viewing the whole system from a great distance, the basic arrangement might be easier to understand. You would see the broad disk of our galaxy. You would see Sagittarius moving on a highly inclined orbit rather than travelling neatly inside the disk. Stretching away from the dwarf would be long regions of tidal debris, with material extending ahead of the surviving remnant and more material following behind. Parts of those arms would have been stripped relatively recently. Other parts would have been travelling independently for much longer. Some debris would already have wrapped around a substantial fraction of the Milky Way. From Earth, we have none of that convenient perspective. We are sitting inside the disk, about 26,000 light-years from the galactic centre, trying to understand a structure that surrounds the galaxy containing us. This creates one of the recurring difficulties in Milky Way astronomy. We know far more about individual stars in our own galaxy than we do about individual stars in most other galaxies, because they are close enough to measure in detail. But understanding the large-scale shape of our galaxy can actually be harder because we cannot step outside it and take a photograph. Imagine trying to map the entire road network of a country while standing on one road and never being allowed to leave the ground. You could measure directions, you could measure distances, you could watch traffic. You could build an excellent map eventually. You would probably still become slightly jealous of anyone allowed to use a satellite. The Sagittarius stream presents this problem on an even larger scale because its stars do not occupy one simple distance from us. One section may pass comparatively close to the Sun, another may reach far into the galactic halo. The leading and trailing material occupy different parts of the orbit. Older debris can overlap younger debris when projected onto the sky. Two groups of Sagittarius stars can appear in almost the same direction, while actually sitting at very different distances. The opposite can also happen. Stars that belong to the same continuous tidal structure may appear separated by huge angles across the sky. A flat star map therefore shows only part of the story. To reconstruct the stream properly, astronomers need several dimensions of information. They need a star's position on the sky. They need its distance. They need to know how it moves sideways across the sky. They need its motion toward or away from us. They often want its chemical composition as well. Once those measurements are combined, the river begins to emerge from the surrounding Milky Way population. A major early step came from the 2-micron all-sky survey, or 2MASS, which allowed astronomers to trace luminous M-giant stars associated with Sagittarius over vast areas. Those stars revealed a trailing arm extending more than 150 degrees across the sky and helped establish the enormous scale of the debris. Later surveys added different stellar traces, velocities, distances, and eventually precise proper motions, turning the first broad outline into a much more detailed map. The Sagittarius stream is now recognized as a dominant substructure of the Milky Way's stellar halo. 150 degrees is worth pausing over. A full circle contains 360 degrees. The Moon appears about half a degree wide. A stream extending 150 degrees across the sky spans the equivalent angular width of roughly 300 full moons placed side by side, and that measurement refers to one broad section of the Sagittarius debris rather than the full history of material stripped from the dwarf. This is why describing Sagittarius only by the surviving core gives a misleading impression. The dwarf galaxy we can still identify near the constellation. Sagittarius is more like the remaining knot at the centre of a much larger disrupted system. A considerable part of what once belonged to the galaxy is now distributed around the Milky Way. Those stars have not been destroyed. They have been reassigned. They once orbited mainly within Sagittarius. Now they orbit mainly within the Milky Way. The transition from one to the other happened gradually, star by star, as tidal forces pushed their trajectories beyond the dwarf's ability to retain them. The leading arm and trailing arm are the two most obvious large-scale products of that process. The trailing arm extends behind Sagittarius along its orbital path. Material in this arm has typically moved onto orbits that cause it to fall progressively behind the surviving dwarf. The leading arm contains stars that have moved ahead. Because Sagittarius has completed repeated passages around the Milky Way, neither arm should be imagined as one group of stars stripped on one particular afternoon several billion years ago. Each contains material associated with different episodes of mass loss. That creates wraps. A wrap is essentially a section of tidal debris that has travelled far enough around the Milky Way to trace another portion of the orbit. If disruption continues through several orbital cycles, stars lost at earlier times can complete more of their galactic journey than stars lost recently. Place all of those populations on one map, and the stream begins to resemble overlapping loops rather than one clean arc. The three-dimensional geometry can become complicated very quickly. Suppose Sagittarius passes close to the Milky Way and loses a group of stars. Those stars begin spreading along the orbit. Sagittarius travels onward. Hundreds of millions of years later, it returns for another strong encounter and loses another population. The first group has now moved much farther away. The second group begins forming younger tidal arms closer to the dwarf. After another orbit, more stars leave. Eventually, several generations of debris occupy different positions around the Milky Way at the same time. Astronomers looking at the sky today are therefore seeing the accumulated results of several periods of stripping. They are not simply mapping where Sagittarius is, they are mapping where Sagittarius used to be and where its escaped stars have travelled since. This makes distance measurements especially valuable. A stream seen only in 2 dimensions could be mistaken for a curved line drawn across the celestial sphere. Once distances are added, researchers can see the structure rising and falling through the galactic halo. Parts of the Sagittarius stream travel tens of thousands of light-years above or below the Milky Way's disk. Some sections reach distances of roughly 60 kiloparsecs from the galactic centre, although the precise extent depends on which debris population and model is being discussed. That is close to 200,000 light-years. The visible disk of the Milky Way is much smaller than the volume occupied by its extended halo. Sagittarius debris takes advantage of that space. Its orbit carries it through the halo on a path tilted strongly relative to the galactic disk, which is one reason its tidal material can appear over such a large area of our sky. There is also an interesting practical result of this geometry. You may have Sagittarius stars relatively near your part of the Milky Way without having any obvious sign that they are visitors. A stream star looks like a star. There is no visible thread connecting it to the dwarf. 2 stars sitting beside one another in an image can have completely different origins. One may have formed in the Milky Way, the other may have formed inside Sagittarius billions of years ago and later been stripped away. Only additional measurements reveal the difference. Astronomers often rely on motion because members of a stream tend to share a coherent orbital pattern. This is where Gaia transformed the study of the galactic halo. Gaia measured extremely precise positions and proper motions for enormous numbers of stars. Proper motion is the tiny apparent movement of a star across the sky, caused by its actual motion through space. For distant stars, that movement can be extremely small. A star might shift by only a tiny fraction of a degree over many years. Gaia was built to measure exactly these sorts of motions with extraordinary precision. Once proper motions are available, a crowded patch of sky stops being merely a crowded patch of sky. Some stars move one way, others move another. Groups begin to separate dynamically. The stream becomes visible in motion. Studies combining Gaia data with distance and stellar population information have recovered Sagittarius as one of the dominant coherent structures in the outer galactic halo. Large samples now allow researchers to trace not only the main arms, but also finer details inside them. One of those details is that the Sagittarius stream splits. In parts of the sky, instead of one band of Sagittarius stars, astronomers see two roughly parallel branches. This feature is usually called the bifurcation. The northern stream was known to divide into a brighter branch and a fainter branch, and later observations found comparable complexity in the southern sky. That immediately caused trouble for simple models. A basic tidal disruption simulation can produce leading and trailing tails quite naturally. Producing the exact branching seen in Sagittarius, while also getting the distances, motions, densities, and other properties correct, is much harder. Several explanations have been proposed. Perhaps the branches represent material stripped during different passages. Perhaps the original Sagittarius galaxy possessed internal rotation. Perhaps different wraps overlap in projection. Perhaps the Milky Way's gravitational environment altered successive generations of debris differently. The important point is that the bifurcation is real structure, not simply a fuzzy edge caused by poor observations. Gaia-based work using more than 700,000 candidate Sagittarius stars has identified 4 broad branches, with bifurcations visible in both hemispheres. That study interpreted the brighter and fainter branches as debris stripped during different close passages of Sagittarius, although the physical reason those generations became misaligned remains an active modelling problem. 700,000 candidate stars sounds enormous until you compare it with the total number of stars in the Milky Way. Then it becomes a very carefully selected needle collection, extracted from a haystack containing hundreds of billions of other needles. This is why finding stream members requires more than simply selecting every star near a line on the sky. Researchers can combine proper motion, colour, brightness, distance, radial velocity and chemical abundance information. Each measurement removes some imposters. A likely Sagittarius star should not merely sit in the right direction. It should also move in a way compatible with the stream. Its distance should make sense. Its stellar properties should fit populations known to exist in Sagittarius. The more pieces agree, the more confident astronomers can become. Chemical composition is particularly useful because the stream does not contain a perfectly uniform population. Sagittarius experienced an extended history of star formation and chemical enrichment before losing much of its material. Different regions of the original dwarf likely contained stars with somewhat different average metallicities. Tidal stripping then removed those regions at different times. As a result, chemistry changes along parts of the stream. Measurements of the trailing arm have found a metallicity gradient, with stars becoming more metal-poor along a long section of the debris. One spectroscopic study measured a change from around -0.59 dex to -0.97 dex over 142 degrees of the trailing arm. The exact numbers matter less here than what they imply. The stream still preserves information about the internal structure of Sagittarius before the Milky Way dismantled it. The outer material of the progenitor could be stripped earlier. More central populations could be removed later. Several billion years afterward, astronomers examine stars distributed across the galactic halo and recover part of the original dwarf's internal arrangement. That is a remarkable amount of information to survive a galactic disruption. It also means the stream is not one homogeneous rope of identical stars. Different sections can represent different ages of debris, different metallicities, different passages, different orbital histories, different responses to the Milky Way's gravity. Even the leading and trailing arms do not reach identical maximum distances from the galactic centre. Astronomers can identify points called apocenters, the parts of an orbit where material reaches its greatest distance from the galactic centre before beginning to fall inward again. The Sagittarius leading and trailing debris have different observed apocentric distances. That difference tells researchers something about how the orbit has evolved and about the gravitational field acting on the debris. It also became one of the reasons Sagittarius proved difficult to reproduce with simple models. If you design a Milky Way model that explains one feature, another feature has an annoying habit of disagreeing. Perhaps the sky position looks right, but the velocities are wrong. Perhaps the leading arm fits, but the trailing arm does not. Perhaps the overall shape works, but the bifurcation disappears. Perhaps the younger debris behaves while older wraps refuse to cooperate. Sagittarius is scientifically useful partly because it is not simple. A perfectly simple stream might tell us less. Every mismatch forces astronomers to ask which assumption needs changing. The Milky Way's mass may be different. The dark matter halo may have a different shape. Sagittarius may have started with more mass. Its internal structure may have been more complicated. Its orbit may have changed significantly during disruption. Another large satellite may be disturbing the entire system. That last possibility has become especially important because the Milky Way is not interacting only with Sagittarius. The Large Magellanic Cloud is also present. The LMC is much more massive than many of the Milky Way's satellite galaxies, and its gravitational influence cannot always be ignored. As the LMC moves through the Milky Way's halo, it affects both the Milky Way and other objects orbiting within it. That includes the Sagittarius stream. So, a star stripped from Sagittarius may respond to the gravity of the Milky Way, the changing position of the Milky Way itself, and perturbations connected with another satellite. No wonder the stream does not draw a perfectly tidy curve. Astronomers once hoped that the orbit of Sagittarius could provide a relatively straightforward measurement of the shape of the Milky Way's dark matter halo. The idea made sense. Follow a long stream, see how its orbit bends, work backward to determine the gravitational field. In practice, different sections of the stream seem to favour different halo shapes, leading to years of debate over whether the Milky Way's halo was approximately spherical, flattened, elongated, or triaxial. More complete models showed that Sagittarius cannot always be treated as a light test particle, moving around a fixed Milky Way. Its own mass mattered. The Large Magellanic Cloud mattered. The Milky Way's response mattered. Older and younger debris behaved differently. The experiment turned out to include several moving pieces. This is not unusual in astronomy. The universe frequently responds to a beautifully simple idea by saying yes, but there are 6 additional complications. The stream remains valuable because each complication leaves its own signature. The broad orbital path tells us about the overall galactic potential. The stream's width carries information about Sagittarius and its internal velocities. The positions of the leading and trailing arms reflect different orbital energies. The apocenters contain information about the orbit and galactic mass. The bifurcations preserve differences between stripping events or structures inside the progenitor. Chemical gradients reveal how the original dwarf stellar populations were distributed. Perturbations may record the influence of massive objects such as the Large Magellanic Cloud. One structure can therefore be used to investigate several parts of galactic history at once. The stream also demonstrates how misleading the visible Milky Way can be. Look at a photograph of our galaxy from Earth, and most of the light is concentrated in the familiar band of the galactic disk. That is where large numbers of stars, gas clouds, and bright star-forming regions sit. The halo appears almost empty, but almost empty is not empty. The halo contains globular clusters. Satellite galaxies move through it. Dark matter dominates much of its mass, and scattered across it are stellar streams produced by systems that the Milky Way has been dismantling. Sagittarius is the most obvious large example, but it is not alone. Nearly 100 stellar streams have been catalogued around the Milky Way, produced by disrupted dwarf galaxies and globular clusters. Sagittarius stands out because of its scale, complexity, and the fact that its surviving progenitor is still identifiable. This means the Milky Way's halo is not simply a quiet outer layer surrounding a finished galaxy. It contains evidence of assembly. Some structures are ancient enough that their stars have become widely mixed. Others remain relatively coherent. Sagittarius is giving us a particularly clear view of the middle of that process. The dwarf has not disappeared. The debris has not fully mixed into the halo. We can still connect the two. Given enough time, that will become harder. Stars in the stream will continue moving on slightly different orbits. Small differences accumulate. The debris becomes more spread out. Interactions with other structures perturb it. Eventually, the distinct Sagittarius signature becomes less obvious. The stars themselves survive, but the neat relationship identifying them as one former galaxy weakens. This gradual loss of structure is often described as phase mixing. Imagine releasing a small group of runners around a circular track, each travelling at a slightly different speed. At first they remain clustered. After several laps they spread around the track. Wait long enough and they can occupy almost every position. The runners have not vanished. The original group has simply become difficult to recognise from position alone. The galactic halo does something similar with accreted stars. That is what makes Sagittarius especially fortunate from our perspective. We are observing it while the trail is still obvious enough to reconstruct. Not at the beginning, not at the end, somewhere in between. The stream lets us see how stars move from membership in a small galaxy into membership in the Milky Way. There is no ceremony marking the change. Once stripped, the star simply follows its new galactic orbit. Millions or billions of years later, a survey records its light. Its motion is measured, its chemistry is examined. A computer compares it with thousands of other stars. And somebody realizes that this apparently ordinary point of light was born in another galaxy. The sky above Earth therefore contains pieces of Sagittarius spread across directions that seem unrelated to one another. Some of those stars passed through the dwarf's history together. They experienced its star formation. They orbited inside its gravitational field. Different layers of debris exist because Sagittarius has not encountered the Milky Way only once. The dwarf has been making repeated passages through the galaxy for billions of years, losing material, changing its orbit, and returning in a progressively altered state. The interaction we see today is the accumulated result of several encounters rather than one isolated collision. Calling those encounters collisions can create a misleading picture. Sagittarius does not approach the edge of the Milky Way, strike something solid, bounce away, and come back later with a dent in the front. The Milky Way has no solid edge. Its disk contains stars, gas and dust spread across enormous distances, while its dark matter halo extends much farther still. Sagittarius moves through that gravitational environment continuously. At certain points in its orbit, though, the encounter becomes much more intense. When Sagittarius comes closer to the centre of the Milky Way, the gravitational field becomes stronger. When its path carries it through the galactic disk, the dwarf passes through a region containing much more concentrated ordinary matter than the outer halo. These close approaches and disk crossings can strongly disturb Sagittarius and can also disturb the Milky Way. Then Sagittarius keeps moving. It travels outward again. The distance between the dwarf and the central regions of the Milky Way increases. The tidal stress becomes less severe. For a while, what remains of the dwarf continues along its orbit without experiencing the same level of disruption. Eventually, gravity brings it back. This repeating journey is central to understanding why the Sagittarius stream is so large. One passage can remove stars. Several passages can distribute those stars around a substantial fraction of the Milky Way. The earliest encounter in the sequence we can reconstruct began when Sagittarius was much more massive than the remnant we observe today. Exactly how massive remains uncertain because we are trying to infer the original galaxy after billions of years of stripping. Different models begin with different progenitor masses, sometimes far larger than the present-day stellar system. That initial mass matters because a larger Sagittarius would have affected its own orbit differently and would have exerted a stronger gravitational influence on the Milky Way. A more massive satellite also experiences an effect called dynamical friction. Despite the name, this does not involve anything rubbing against anything else. Space has once again declined to behave like an ordinary household object. Dynamical friction happens because a massive object moving through a population of stars and dark matter gravitationally disturbs the material around it. Imagine Sagittarius moving through the Milky Way's dark matter halo. As it passes, its gravity slightly alters the trajectories of surrounding particles and stars. A gravitational wake develops behind it. That wake then pulls backward on Sagittarius. The dwarf loses orbital energy and angular momentum. Over long periods, its orbit can shrink. The effect is more important for a more massive satellite, because a massive object creates a stronger gravitational disturbance. So the Sagittarius of several billion years ago may not have followed exactly the same orbit as the small remnant does today. Its early passes may have occurred farther out. As dynamical friction removed orbital energy, later passages could carry the dwarf deeper into the Milky Way. At the same time, tidal stripping was reducing Sagittarius's mass. This creates a changing relationship. When Sagittarius was heavier, dynamical friction could alter its orbit more effectively. As it lost material and became lighter, the effect weakened. The orbit evolved while the satellite itself evolved. That makes reconstructing the past considerably more difficult than simply running today's orbit backward like a video. If you know the present position and velocity of an object moving in a perfectly fixed gravitational field, reversing its trajectory is mathematically straightforward. Sagittarius refuses to offer that convenience. Its mass changed. The Milky Way changed. The galactic disk responded to the encounters. The Large Magellanic Cloud also influenced the gravitational environment. Stars were stripped away. Dark matter was stripped away. The orbit itself evolved. Running the system backward therefore requires assumptions about what Sagittarius looked like before the evidence we now see was created. Researchers test those assumptions with numerical simulations. They begin with a model Sagittarius and a model Milky Way. They assign Sagittarius an initial mass, internal structure, and orbit. Then they allow gravity to operate over billions of simulated years. The dwarf approaches the Milky Way. Tidal forces remove material. The remaining object continues around its orbit. It returns, more material is removed. Eventually a stream forms. The final simulated system can then be compared with the actual Sagittarius remnant and the observed debris. A successful model needs to reproduce far more than the dwarf's location today. The stream should appear in approximately the correct parts of the sky. Its stars should have realistic distances. The leading and trailing arms should move at the correct velocities. The locations of distant debris should make sense. The remnant should survive with properties resembling the real Sagittarius. Ideally, the same model should also produce disturbances in the Milky Way consistent with what astronomers observe. That is a long list of requirements for a dwarf galaxy that has already spent several billion years making the problem worse. One influential picture of the recent interaction involves several major passages over roughly the last 6 billion years. A 2020 analysis of Gaia data found distinct periods of enhanced star formation in the Milky Way approximately 5.7 billion, 1.9 billion, and 1 billion years ago. Those times broadly coincide with proposed close passages of Sagittarius in orbital models. This does not mean astronomers watched Sagittarius cross the disk 5.7 billion years ago. There was nobody available with a telescope. The timing is reconstructed. Researchers study the ages of Milky Way stars and identify periods when star formation increased. Separately, simulations of Sagittarius estimate when strong encounters occurred. When the two histories line up, one possibility is that the passages of Sagittarius helped trigger those bursts of star formation. The mechanism is plausible. because a satellite passing through or near a galactic disk can gravitationally disturb the disk's gas. Gas that had been moving relatively calmly can be compressed. Density waves can develop. Regions can become unstable. Under suitable conditions, clouds of gas collapse and form new stars. Sagittarius does not bring a box of stars with it and distribute them through the disk. It can disturb material already present in the Milky Way strongly enough to change what that material does. A useful analogy is a container of water with sediment resting near the bottom. Pass something through the water and the disturbance can rearrange material far beyond the exact path of the object. The object does not have to touch every grain. It changes the motion of the system around it. A galactic disk responds through gravity rather than ordinary fluid motion alone, but the principle that a localized disturbance can produce a much larger response is helpful. The proposed first of those major encounters occurred around 5 or 6 billion years ago. Sagittarius at that time would have been substantially more massive than it is now. The Milky Way was also not identical to the Milky Way we inhabit today. Galaxies continue evolving. Their disks grow, stars form and die. Gas is added, consumed, expelled, and redistributed. Satellite systems change. So this was an encounter between two earlier versions of the galaxies we now observe. During that passage, Sagittarius would have experienced strong tides. Material in its outer regions could be pulled away. The Milky Way's disk could be disturbed. Sagittarius then continued along its orbit, but it no longer contained exactly the same stars and dark matter that it carried before the encounter. The next trip began with a reduced galaxy. This is an important part of the repeated passage story. Sagittarius does not reset between encounters. Damage accumulates. Imagine taking the same object through a stress test several times, while removing pieces after each test. The second test acts on a different object from the first. The third acts on something weaker still. For Sagittarius, the most loosely bound material tends to leave first. Its extended dark matter halo would have been particularly vulnerable. Stars in the outskirts could then be removed. Later passages acted on a system whose mass distribution had already been changed. Each return could expose material that had previously been better protected inside the dwarf. This helps explain why different parts of the stream can contain somewhat different stellar populations. Older debris may include stars that once lived farther from the centre of Sagittarius. More recently stripped stars may have come from regions deeper inside the progenitor. Chemical differences along the stream can therefore contain information about the order in which the galaxy was dismantled. After the earlier encounter, Sagittarius travelled through another large portion of its orbit before returning. The period between passages is not fixed like the second hand of a clock because the orbit evolves. Still, the broad sequence gives astronomers a way to connect debris with separate episodes. Material lost during one passage spreads along the orbit. Before it has completely mixed into the Milky Way halo, Sagittarius returns and releases another generation. Now, two groups are evolving at once. Repeat that several times, and the stream acquires overlapping structures of different ages. This is why astronomers can sometimes speak of debris removed 1, 2, or several pericentric passages ago. Pericenter is the point in an orbit where an object comes closest to the body it is orbiting. For Sagittarius, a pericentric passage brings the dwarf into the region, where the Milky Way's tidal influence can become especially severe. The opposite point, where Sagittarius reaches the greatest distance on a given orbit, is the apocenter. A highly simplified trip would therefore go something like this. Sagittarius falls inward. Its speed increases as it enters the deeper gravitational field of the Milky Way. It reaches pericenter. Tidal forces intensify. Stars and dark matter can be stripped. The dwarf travels away again. It slows as it climbs outward. At apocenter, its inward motion begins again. Then the process repeats. The real path is more complicated, but this basic inward and outward cycle helps explain how Sagittarius can keep returning without simply flying away after one encounter. It is gravitationally bound to the Milky Way. Unless the interaction gives the dwarf enough energy to escape, the orbit brings it back. Unfortunately for Sagittarius, being gravitationally bound to the object dismantling you is not an ideal arrangement. By the time of the later passages, the dwarf had already created long tidal tails. The Milky Way was therefore interacting with two versions of Sagittarius at once. There was the compact remnant returning toward the disk, and there was older debris already spread around the halo. The older stars continued orbiting independently, while new stars were added to the stream. The surviving dwarf could pass through a region of the galaxy, while material stripped on an earlier orbit was somewhere completely different. All of it still belonged to the same historical event. Around 2 billion years ago, another proposed major interaction coincides with a second period of enhanced star formation, identified in the Gaia-based reconstruction of the Milky Way's local stellar history. Then another strong event occurred around 1 billion years ago. Again, Sagittarius would have arrived smaller than before. Again, it could disturb the galactic disk while losing more of itself. Researchers have also studied evidence for more recent interactions, including passages within the last several 100 million years. Those later events are especially interesting because the Milky Way still carries dynamical signatures that may not have had enough time to disappear. A galaxy disk is not perfectly rigid. If something massive perturbs it, stars can begin moving vertically above and below the disk. Radial motions can also be excited. Waves can travel through the stellar population. Different regions respond at different rates. Over time, those motions wind into patterns in position and velocity. Gaia has allowed astronomers to see those patterns with extraordinary detail. One of the most famous is the phase-space spiral discovered in Gaia data near the Sun. Instead of plotting stars only by their positions on the sky, researchers can compare a star's vertical position relative to the galactic disk with its vertical velocity. The distribution is not perfectly smooth. It forms a spiral-like structure. That feature indicates that the local disk has been disturbed and has not yet fully returned to equilibrium. Imagine striking a bell. Long after the initial impact, vibrations remain. By studying those vibrations, you may learn something about when the bell was struck. The galactic disk is not a bell, but the same broad logic applies. A perturbation changes stellar motions. Those motions evolve in predictable ways. If simulations reproduce the patterns observed by Gaia, researchers can estimate when the disturbance occurred and what might have caused it. Sagittarius is one of the leading suspects. N-body simulations have shown that repeated Sagittarius impacts can excite vertical and radial oscillations in the Milky Way disk, resembling several structures found in Gaia observations. Some models connect a relatively recent pericentric passage with disturbances that developed several 100 million years ago. This does not mean every unusual feature in the Milky Way disk was produced by Sagittarius. The galactic bar can affect stellar motion. Spiral structure can affect it. The Large Magellanic Cloud contributes gravitational disturbances. Internal evolution matters. Separating all of these effects is one of the major challenges in galactic dynamics, but Sagittarius is large enough, and its interaction is well established enough that it cannot simply be ignored. The important change in our understanding is that the dwarf is no longer viewed only as a victim of the Milky Way, it is also a perturber. Yes, the Milky Way is tearing Sagittarius apart. The difference in scale is enormous. The smaller galaxy will lose this encounter in the long run. But losing does not mean having no effect. Each time Sagittarius has approached the galactic disk, its gravity has acted on the Milky Way's stars, gas and dark matter. The Milky Way has responded. A smaller satellite can produce ripples in a much larger disk because galactic disks are dynamic systems rather than solid structures. Push one region gravitationally and the response can propagate. This may help explain vertical waves observed in the disk. It may contribute to variations in stellar density. Some simulations have even investigated whether repeated encounters with Sagittarius could influence the Milky Way's spiral structure. That idea is still more complicated than simply saying Sagittarius created the spiral arms. Spiral galaxies can develop structure through several mechanisms, and the Milky Way's exact spiral history is not fully reconstructed. Still, satellite interactions are capable of exciting spiral patterns, and Sagittarius has repeatedly supplied the sort of perturbation that can matter. Its effect on star formation is similarly intriguing but should be described carefully. The Gaia-based study found enhanced star formation episodes whose timing corresponds closely with proposed Sagittarius passages. That correlation supports the idea that Sagittarius helped trigger star formation. It does not allow us to identify every individual star produced because of the dwarf. The Sun formed about 4.6 billion years ago, not dramatically long after the earliest of those proposed major interactions. This has led researchers to note the possibility that Sagittarius indirectly contributed to conditions that eventually produced the Sun. It is an interesting possibility. It is not evidence that Sagittarius specifically created the solar system. We cannot identify the exact ancestral gas cloud, rewind it several billion years, and watch Sagittarius give it a helpful gravitational nudge. What we can say is that the timing overlaps with a period when the Milky Way appears to have experienced increased star formation following one of the proposed major Sagittarius interactions. That places our own existence inside the broader history of galactic evolution without requiring the universe to have planned any of it. Sagittarius did not cross the Milky Way because Earth needed somewhere to appear several billion years later. Gravity is not known for that level of project management. The repeated encounters also help astronomers estimate how long Sagittarius can survive. Every strong passage removes more material. The dwarf becomes progressively less massive. Its central remnant may remain bound for some time, but the present configuration cannot continue unchanged forever. Eventually, the remaining system may be disrupted so thoroughly that Sagittarius ceases to exist as a recognizable dwarf galaxy. Its stars will not disappear when that happens. They will join the stream and, over longer periods, the broader stellar halo of the Milky Way. The result will resemble other ancient accretion events that astronomers now reconstruct from stellar motions and chemistry. We happen to see Sagittarius before that final stage. The stream is already enormous, but the source still exists. Its repeated returns let us connect sections of debris with successive stages of destruction. Earlier passages removed one set of material, later passages removed another. The present remnant shows what survived all of them. This also means that measuring only the dwarf's current mass tells us very little about the force of its oldest encounters. The Sagittarius that first strongly disturbed the Milky Way may have been dramatically more massive. Researchers therefore use the stream and the galactic disk together to constrain its history. The amount of debris tells us how much material was lost. The width and velocity structure of that debris carry information about the progenitor. The orbit tells us where strong interactions occurred. The Milky Way's response provides another clue to how massive the dwarf may have been at different times. A model with Sagittarius too light may fail to disturb the disk enough. A model with it too heavy may create effects stronger than those observed. A model with the wrong orbit may produce disturbances at the wrong times. A model with the wrong mass loss history may place stream stars in the wrong regions. Everything is connected. The stream records what happened to Sagittarius. The disk records some of what Sagittarius did to the Milky Way. Put them together and the interaction becomes a two-sided history. That is one reason Gaia has become so important. Before precise measurements of stellar motion were available on this scale, many galactic disturbances were difficult to recognize clearly. Gaia does not watch the Milky Way physically ripple in real time. The motion is far too slow for that. Instead, it measures the positions and velocities of enormous numbers of stars accurately enough that the collective pattern becomes visible. A single star moving slightly upward through the galactic disk means very little. Millions of stars showing coordinated motions mean something happened. The same logic applies to Sagittarius debris. One unusual halo star proves almost nothing. Thousands of stars sharing related positions, distances, velocities, and chemical properties reveal a structure. Galactic archaeology works by finding order inside enormous amounts of stellar information. The repeated orbit of Sagittarius gives that order a timeline. Some stars were stripped recently. Others have been travelling around the Milky Way for several billion years. Some disk stars may preserve the dynamical consequences of later impacts. Older signatures may have become mixed or overwritten by subsequent evolution. The interaction therefore contains multiple clocks, none of them conventional. The location of tidal debris tells us how long it has been spreading. The winding of patterns in the galactic disk tells us how long stellar populations have been phase mixing. Stellar ages reveal when bursts of star formation occurred. Computer simulations connect those separate measurements with proposed passages of the dwarf. No single measurement provides the complete history. Together they narrow the possibilities. There is also something slightly misleading about saying Sagittarius keeps coming back, because from Sagittarius's perspective, it never really leaves the Milky Way's influence. Even at the more distant parts of its orbit, it remains inside the galactic halo. The Milky Way's gravity is always acting on it. The difference is intensity. At greater distances, tidal forces across the dwarf are weaker. Near pericenter and during passages through the galactic disk, the gravitational environment changes rapidly, and disruption becomes more severe. So the interaction is continuous, with occasional periods of much stronger stress. Those periods create the landmarks astronomers try to date. 5 or 6 billion years ago, around 2 billion years ago, around 1 billion years ago. More recent passages measured in hundreds of millions of years. The exact history varies between models, and improved measurements continue to refine it. But the overall pattern remains clear. Sagittarius has returned more than once. It has lost material more than once. The Milky Way has been disturbed more than once, and the stream around us is a mixture of the evidence left by those repeated encounters. That is where the history becomes a data problem. Sagittarius has been making repeated passes around the Milky Way, but astronomers do not have recordings of those encounters. There are no photographs from 2 billion years ago showing the dwarf halfway through the galactic disk, and there is no logbook telling us which stars escape during each passage. Everything has to be reconstructed from what survives today. Fortunately, stars keep records surprisingly well. They keep them in where they are. They keep them in how they move. They keep them in the elements inside their atmospheres. They keep them in their ages. And when astronomers combine enough of those measurements, stars that look unrelated on the sky can begin to tell the history of the same disrupted galaxy. This kind of work is often called galactic archaeology. The name is appropriate because the goal is not simply to describe the Milky Way as it looks today. Astronomers use present-day evidence to reconstruct earlier events. An archaeologist might examine layers of soil, fragments of pottery, building foundations, and tools to infer how a settlement changed over time. A galactic archaeologist works with positions, velocities, stellar ages, and chemical abundances. The ruins are considerably farther apart. That is one inconvenience. Another is that the ruins are moving at hundreds of kilometers per second. The Sagittarius stream is a particularly useful archaeological site, because the event that created it is not completely ancient and erased. The parent galaxy still survives. Large parts of its tidal debris remain coherent. Stars stripped at different times occupy different regions of the stream. This gives astronomers something close to a sequence of evidence from different stages of the same disruption. The first task is identifying which stars actually belong to Sagittarius. That sounds straightforward until you look at the Milky Way. There are hundreds of billions of stars in our galaxy. From Earth, the sky projects all of them onto 2 dimensions. A star that appears next to another star may actually sit thousands of light years closer or farther away. They can belong to completely different populations, while looking almost identical in an ordinary image. Sagittarius debris makes the problem more difficult because the stream is broad and faint. You cannot draw a line around it and assume every star inside came from the dwarf. Most did not. A patch of sky containing Sagittarius debris also contains Milky Way disk stars, halo stars, and sometimes stars associated with other structures. Astronomers therefore need filters that separate likely stream members from everything else. Position is the simplest filter. If models and earlier observations show that the Sagittarius stream crosses a certain region, stars there become candidates. But position alone is weak evidence. Imagine standing beside a motorway and deciding that everyone visible nearby must have arrived in the same car. You would collect an interesting group, but not a useful one. Distance makes the selection better. Suppose many stars in one direction appear to lie at approximately the distance expected for a section of the Sagittarius stream. Now the group becomes more interesting. Astronomers estimate stellar distances in several ways. For nearby stars, parallax is extremely useful. As Earth moves around the Sun, a nearby star appears to shift slightly relative to more distant background objects. Measure that tiny shift and geometry gives you the distance. For more distant halo stars, parallax becomes increasingly difficult, because the angle becomes extremely small. Researchers can instead use certain types of stars whose intrinsic brightness is known, or can be estimated. RR Lyrae stars are especially valuable for this. RR Lyrae stars are old pulsating stars. Their brightness changes in a predictable way, and their intrinsic luminosities can be calibrated well enough to make them useful distance indicators. If you know roughly how bright a star really is, and measure how faint it looks from Earth, you can estimate how far away it must be. The same basic idea works with other suitable stellar tracers. Different surveys therefore use different populations depending on what part of the stream they are trying to map. M giants are useful because they are luminous and can be selected efficiently in infrared surveys. K giants can be detected at large distances and studied spectroscopically. Blue horizontal branch stars are useful tracers of older, more metal-poor populations. Main sequence turn-off stars are much more numerous, which makes them useful for tracing faint structure, even though individual distances can be less precise. RR Lyrae provides strong distance information. No single type of star tells the entire story. Using several populations helps because each one samples Sagittarius differently. This becomes important when the dwarf contains stars of different ages and metallicities. M giants, for example, tend to trace a younger and more metal-rich population than some of the older halo tracers. If astronomers mapped Sagittarius only with M giants, they might obtain an excellent map of that population, while missing parts of the dwarf's older history. That is one reason the picture became more complicated as additional surveys arrived. The first maps revealed the broad stream, later tracers revealed branches, older debris, chemical differences, and structures that the earlier samples had not shown clearly. Distance gives astronomers a third dimension, but motion is what makes the stream much easier to distinguish. A star does not need to remain physically close to Sagittarius to preserve evidence of its origin. Its orbit can still resemble the orbits of other stripped stars. Astronomers measure stellar motion in two broad parts. The first is radial velocity. That is the component of motion directly toward or away from us. It is measured using the Doppler effect. When a star moves toward Earth, features in its spectrum shift slightly toward shorter wavelengths. When it moves away, they shift toward longer wavelengths. The same principle explains why the pitch of an ambulance siren changes as it approaches and passes you, although stars have fortunately chosen a quieter method. Measure the wavelength shift of known spectral lines, and you can calculate the star's radial velocity. Now imagine doing that for hundreds of stars along the suspected Sagittarius stream. If the stars are unrelated, their radial velocities may show a broad mixture of galactic motions. If many of them belong to one tidal structure, a pattern appears. Velocity changes progressively along the stream. Stars in one section approach us at related speeds. Farther along, the velocity changes as the stream curves through its orbit. That continuous trend is difficult for random foreground contamination to imitate. The second type of motion is transverse motion, meaning movement across the sky. From our perspective, distant stars barely seem to move at all. But with precise measurements collected over time, their positions shift. That tiny angular change is called proper motion. Gaia dramatically improved this part of the investigation. By measuring positions and motions for enormous numbers of stars, Gaia gave astronomers a way to examine the Milky Way in what is called phase space. In its full form, phase space combines 3 dimensions of position with 3 dimensions of velocity. Where is the star, and how is it moving? 2 stars may be separated by a large distance and still occupy related orbits. 2 stars may sit close together while moving in completely different directions. Once motion is added, structures hidden in ordinary sky maps become much easier to find. The Sagittarius stream is one of the clearest examples. Its stars do not simply form a density enhancement, they form a moving density enhancement. Take thousands of candidate stars and compare their proper motions. A coherent pattern emerges along the stream, add radial velocities, and the 3-dimensional motion becomes much better constrained. Add distance estimates and astronomers can reconstruct where different sections sit around the galaxy. Instead of a faint stripe across the sky, researchers obtain part of an orbit. This is already enough to do useful archaeology. Stars farther along an older wrap have generally been separated from Sagittarius, longer than stars recently stripped near the surviving dwarf. Their current positions and motions can therefore be compared with simulations to estimate when they escaped. But there is another source of information that does not depend only on gravity. Astronomers can examine what the stars are made of. A star's spectrum contains absorption lines produced by different chemical elements in its atmosphere. Iron leaves one set of features. Magnesium leaves others. Silicon, calcium, carbon, aluminum, nickel, and many more elements can be measured under suitable conditions. From those lines, researchers estimate chemical abundances. These abundances act as records of the environment in which the star formed. Stars do manufacture new elements during their lives, and some types change their surface composition, so the interpretation is not always simple. But for many useful abundance measurements, the basic chemical pattern retains information about the gas from which the star originally formed. That gas carries the history of earlier generations. Massive stars live quickly and explode as core collapse supernova, producing large amounts of certain elements, including what astronomers call alpha elements. Type 1. A supernovae occur on different timescales and contribute substantial iron. As a galaxy evolves, continued star formation and repeated stellar deaths gradually alter the chemistry of its gas. The balance between elements can therefore tell astronomers something about how quickly a galaxy formed stars and enriched itself. Dwarf galaxies often develop chemical patterns different from the Milky Way because their star formation histories are different. This gives astronomers another way to identify immigrants. Suppose a star's orbit makes it a strong Sagittarius candidate. Now suppose its chemical abundances also resemble stars in the Sagittarius core and differ from typical Milky Way populations at similar metallicity. The identification becomes much more convincing. This approach is sometimes loosely described as chemical tagging. The chemistry is not a literal serial number. 2 unrelated stars can have similar abundance patterns. But when chemistry is combined with position and motion, it becomes extremely powerful. Sagittarius is especially useful because researchers can compare stream stars directly with stars still located in the surviving dwarf. The parent population has not vanished completely. Surveys such as Apogee have obtained high-resolution infrared spectra for stars in the Sagittarius core and in its tidal debris. One analysis combined Gaia astrometry with Apogee measurements to identify more than 100 stream stars and compare them with hundreds of stars in the Sagittarius core. The results showed clear chemical differences between the present core and dynamically older stream populations. Older debris was, on average, more metal poor. That fits the idea that Sagittarius once contained an internal chemical gradient. Its outer regions were chemically different from its inner regions. The Milky Way then removed those layers in sequence. Think about what that means. Before disruption, Sagittarius may have had more metal-rich stellar populations concentrated toward its central regions and more metal-poor populations distributed farther out. The first strong episodes of stripping preferentially removed stars in those outer regions because they were less tightly bound. Those stars entered the stream earlier. Later, after Sagittarius had already lost enormous amounts of material, tidal forces began reaching populations that once lived farther inside. Those stars were stripped more recently. Billions of years afterward, astronomers measure chemical differences along the stream and partially reconstruct the original internal structure of a galaxy that no longer exists in that form. This is archaeology in a very literal scientific sense. The present stream contains the former geography of Sagittarius. Not perfectly. The dwarf was dynamic even before disruption. Stars orbited inside it. Material mixed. The interaction itself changed the system, but statistically, the gradients remained strong enough to recover information. A large Gaia-based chemical map published in 2023 used more than 34,000 red giant branch stars to examine metallicity across the Sagittarius stream. The study found systematic chemical variation not only along the stream, but across its width, and comparisons with numerical simulations showed that the observations were consistent with Sagittarius having possessed a significant radial metallicity gradient before disruption. That is an enormous improvement over trying to understand the galaxy from a handful of stars. 34,000 measurements turn a vague chemical trend into a map. Now chemistry can be drawn across the stream in much the same way that distance or velocity can. One area is relatively metal-rich, another is more metal-poor. Different debris populations occupy different regions. The structure on the sky becomes connected with the structure of the original dwarf. This can even help explain why different stellar traces produce slightly different versions of Sagittarius. A survey selecting metal-rich M giants will emphasize one population. A survey using old metal-poor horizontal branch stars will emphasize another. Both can be tracing Sagittarius correctly while showing different parts of its history. The apparent disagreement becomes information. Another useful measurement is stellar age. Dating an individual star precisely is difficult, but astronomers can estimate ages from stellar evolution. Stars change in predictable ways as they consume nuclear fuel. A star's temperature, luminosity, surface gravity, chemical composition, and evolutionary stage can be compared with models to estimate when it formed. For large populations, these ages reveal when the dwarf was actively producing stars. Combine that with chemistry and the picture becomes richer. Older metal-poor stars formed early. Younger populations appeared after Sagittarius had time to enrich its gas. Some of the youngest populations may have formed when the dwarf was already interacting with the Milky Way. By comparing ages inside the remnant with ages among tidal debris, astronomers can ask which generations were present in different regions of the progenitor. Globular clusters add another layer. Sagittarius arrived with several associated clusters, and those clusters have their own ages, chemical compositions and orbital properties. Some remain linked to the remnant. Others can provide evidence of the larger system Sagittarius possessed before disruption. Messier 54, sitting near the centre of Sagittarius, is the most famous example. A globular cluster is easier to study chemically than an extremely diffuse stream because many stars formed within a compact system. Compare those cluster populations with field stars in Sagittarius and the stream, and researchers gain more landmarks in the dwarf's evolutionary history. All of these measurements eventually have to be combined. A useful Sagittarius member might have a sky position, distance, proper motion, radial velocity, iron abundance, magnesium abundance, age estimate, and perhaps several other chemical measurements. One star provides a small amount of evidence. 10 stars provide a pattern. 10,000 stars reveal structure. Hundreds of thousands allow researchers to divide that structure into populations that would otherwise remain blended together. This is why modern galactic archaeology depends so heavily on large surveys. The telescope is important, but the database becomes equally important. A survey may collect information on millions of stars, most of which have nothing to do with Sagittarius. Researchers then search that catalogue for the tiny fraction occupying the appropriate regions of position, velocity, and chemical space. It is less like looking through a telescope until you happen to see the stream, and more like searching an enormous multi-dimensional filing cabinet. Unfortunately, nobody organised the filing cabinet. The Milky Way simply threw everything inside. Computer methods become essential. Researchers apply selection criteria. They calculate probable orbits. They compare angular momenta. They use clustering algorithms to identify groups. They generate simulations and calculate which observed stars lie close to predicted debris. Candidate lists are refined as better data arrives. A star considered a likely member under one method may be rejected when improved proper motion becomes available. Another star that looked ordinary may suddenly match Sagittarius once its radial velocity is measured. This constant revision is healthy. Galactic archaeology is not about forcing every strange star into a known stream. It is about testing whether the evidence agrees. Contamination remains a major issue because some Milky Way stars naturally have positions and velocities similar to Sagittarius debris. Chemistry helps separate them. Multiple velocity components help. Distance helps. The more independent measurements point to the same origin, the stronger the case becomes. Astronomers can then take a carefully selected sample and compare it with disruption models. Here, the archaeological reconstruction becomes a kind of reverse engineering. A simulation starts with a proposed earlier version of Sagittarius. Perhaps the dwarf contains a certain stellar mass. Perhaps its dark matter halo has a particular distribution. Perhaps its metal-rich stars are concentrated near the centre, while metal-poor stars extend farther out. The simulated dwarf is placed on an orbit around a model Milky Way. Gravity is allowed to operate. Stars are stripped. The model stream develops. Researchers then ask whether the artificial debris resembles the real debris. Do the oldest stripped stars appear where real metal-poor stars are found? Does the simulated leading arm have the right velocity? Does the trailing arm reach the correct distance? Does the chemical gradient match? Are the bright and faint branches reproduced? Does the surviving core have the correct structure? A model that answers one question and fails the other 6 is not finished. Sagittarius has been particularly stubborn in this respect. Models have successfully reproduced major parts of the stream while struggling with others. That difficulty has forced astronomers to improve the assumed Milky Way gravitational field, reconsider the mass of the Sagittarius progenitor, account for orbital evolution, and include the gravitational effect of the Large Magellanic Cloud. Better observations make the reconstruction harder before they make it easier. A simple stream can be explained by a simple model. Then a survey discovers that the stream splits. The model needs revision. Spectroscopy reveals a chemical gradient. Now the progenitor needs internal structure. Gaia reveals more precise motions. Some predicted orbits no longer work. Distant traces extend the debris farther into the halo. The model grows again. This may sound frustrating, but it is exactly why the stream is valuable. Every new detail rules out histories that could otherwise have seemed plausible. The debris is gradually narrowing the list of possible pasts. One of the most interesting things astronomers can extract is an approximate stripping time for different stars. They cannot look at a star and directly read, left Sagittarius 1.7 billion years ago. Instead, they compare its present orbit with numerical models. If simulations consistently place stars in that region, after being stripped during a particular pericentric passage, researchers can assign a likely dynamical age to that debris. Now chemistry can be plotted against stripping time. That produces a different kind of history. Instead of asking where metal-poor stars are, astronomers ask whether older debris is systematically more metal-poor than younger debris. Studies using apogee have found exactly this kind of trend. Stars estimated to have been stripped earlier are chemically different on average from the present Sagittarius core. That supports the idea that the dwarf was being peeled from the outside inward. The stream becomes a timeline, not a perfectly ordered one. Stars removed in the same broad event can spread, different wraps overlap, orbital uncertainties remain, but statistically the sequence survives. There is another important reason to map individual stars accurately. Some of the oldest Sagittarius debris may be extremely distant. Older stars have had more time to move away from the surviving remnant and can occupy remote regions of the galactic halo. Finding them gives astronomers access to earlier stages of disruption, when Sagittarius was more massive and less damaged. Those are precisely the stages that are hardest to reconstruct from the present core. The core tells us what survived. The oldest debris tells us what was lost first. Both are needed if we want to understand the progenitor rather than only the wreckage. This is also where Sagittarius becomes part of a much larger story. The Milky Way halo contains debris from many accretion events. Some parent galaxies still exist. Others were destroyed billions of years ago. Their stars are now mixed through the halo, and identifying them requires the same combination of dynamics and chemistry used for Sagittarius. Sagittarius serves almost as a training case. We know the surviving progenitor. We know an enormous stream belongs to it. We can test methods for linking stars back to their origin. Once those methods work, astronomers can apply them to systems where the parent galaxy vanished long ago. A group of halo stars with related motions may be debris. Add shared chemical properties and the case strengthens. Estimate their ages and a history begins to emerge. Calculate their orbits and researchers can infer the type of merger that deposited them. The Milky Way gradually stops looking like one population of stars and starts looking like a combination of populations assembled at different times. Some stars formed inside the galactic disk. Some formed in the early halo. Some arrived inside dwarf galaxies. Some arrived in globular clusters. Some were added so long ago that their original structures have mostly disappeared. Sagittarius happens to be arriving late enough for us to see the process clearly. Its stars are in transition between belonging to an obvious satellite and becoming ordinary members of the Milky Way halo. Wait long enough, and that distinction will become harder to recover. The stream will continue to phase mix. Stars will spread along their orbits. Fine structure will become less obvious. The surviving core will lose more material. Eventually, an astronomer studying the Milky Way in the distant future might encounter Sagittarius only as a complicated population of halo stars with unusual chemistry and related orbital properties. They would have to reconstruct the dwarf much as we reconstruct older mergers today. We have the advantage of arriving while the evidence is still organised. The core remains visible, the stream remains coherent. Different wraps can still be traced. Chemistry still changes systematically across the debris. Proper motions still reveal common motion. Distances still outline the enormous orbit. Every additional star measured adds another small piece. A spectrum gives a velocity. A chemical abundance suggests a birthplace. A pulsating star gives a distance. Gaia supplies proper motion. A simulation estimates when the star was stripped. None of those measurements alone tells the whole history. Together, they let astronomers take a galaxy spread across hundreds of thousands of light years and partially reconstruct the smaller galaxy that existed before the Milky Way began taking it apart. And once the stars of Sagittarius can be used to reconstruct Sagittarius itself, the same measurements can be turned around. Until now, we have treated the stream mainly as evidence of what happened to the dwarf galaxy. Its stars tell us where Sagittarius travelled, which populations were stripped first, and how repeated passages gradually turned a compact galaxy into a long structure around the Milky Way. But the same stars also record something about the Milky Way. Every one of them has spent hundreds of millions, and in some cases billions of years moving through the galaxy's gravitational field. Their trajectories depend on how much mass the Milky Way contains and where that mass is located. If the distribution of mass changes, the orbit of the stream changes with it. That matters because most of the Milky Way's mass is not arranged in the bright disk we see across a dark sky. There are stars in the disk, there is gas, there is the central bulge and bar, there are stellar populations in the halo. Yet observations of galaxies show that visible matter alone cannot explain the gravitational behaviour we measure. The Milky Way is thought to sit inside a much larger halo dominated by dark matter, extending well beyond the bright stellar disk. Dark matter does not emit ordinary light, so astronomers mainly study it through the gravity it produces. That creates an obvious problem. How do you map something you cannot see? You watch what moves through it. If astronomers know the position and motion of an object, gravity determines how its path changes. This is how unseen planets were historically inferred from their gravitational influence. It is how the masses of stars can be estimated from orbiting companions. At galactic scale, the idea remains the same, although the calculation becomes much more difficult. The Sagittarius stream gives astronomers a long collection of test particles distributed through the Milky Way's halo. The stars do not know they're conducting an experiment. They simply orbit. Astronomers measure the results. Consider a very simple imaginary Milky Way containing only the bright disk and central stars. Place Sagittarius in that gravitational field and allow it to orbit. Stars escape from the dwarf and begin forming a tidal stream. Now build a second model with the same visible galaxy, but surround it with a large dark matter halo. The gravitational field changes. Sagittarius follows a different orbit. The locations of the leading and trailing arms change, their velocities change, the distances reached by the debris change. After several passages, the second simulated stream can look very different from the first. Compare both models with the real sky, and one may fit the observations better. Then you adjust the halo again. Make it more massive, less massive, more spherical, more flattened. Change how quickly its density falls with distance. Run the model again. This is the basic idea behind using a tidal stream to study dark matter. The important word there is basic. The actual process became considerably more troublesome. One of the first questions astronomers hoped Sagittarius could answer was the shape of the Milky Way's dark matter halo. The phrase dark matter halo can encourage us to picture a perfectly round cloud surrounding the galaxy. There is no reason it has to be perfectly round. Computer simulations in which dark matter structures grow through gravity often produce halos that are not exact spheres. They can be flattened, stretched, or have three unequal axes. If the Milky Way's halo is flattened or elongated in a particular direction, a stream orbiting through it responds. Its orbital plane can shift. Different wraps can separate differently. The leading and trailing debris can follow paths that would not occur inside a perfectly spherical gravitational field. So astronomers took measurements of Sagittarius and began asking what halo shape could reproduce them. At first, the answers did not agree. Some measurements seemed to favour a nearly spherical halo. Early analyses of the large Sagittarius structures identified in Sloan Digital Sky Survey data found that the geometry could be consistent with a halo close to spherical. That seemed reasonable enough. Put a roughly spherical dark matter distribution around the Milky Way, place Sagittarius inside it, and reproduce the broad stream. Then other observations caused trouble. The position of one arm could be reproduced, but its velocity might not fit. A model might explain the trailing stream while failing to place the leading stream correctly. Change the halo shape to fix the leading arm, and something else would move out of place. For several years, different observations seemed to demand contradictory properties from the same Milky Way. This was not because gravity had changed its mind halfway around the galaxy. It meant the models were missing something. One influential solution proposed that the outer galactic halo was triaxial. Triaxial simply means the shape has three different characteristic axes. A basketball is approximately spherical. A flattened disk has one short axis, and 2 similar long ones. A triaxial shape is more like an object stretched differently in 3 directions. Using this type of dark matter halo allowed researchers to reproduce several major properties of the Sagittarius stream simultaneously. Scientifically, that was interesting. Physically, it also looked unusual. The orientation of the required halo did not fit comfortably with the simplest expectations for how the Milky Way's mass should be arranged relative to its disk. When a mathematical fit demands an unexpected galaxy, there are at least 2 possibilities. The galaxy really is unexpected, or the model has left something important out. In the case of Sagittarius, one of the most important missing pieces turned out to be another galaxy, the Large Magellanic Cloud. We have mentioned the LMC before because it is one of the Milky Way's most substantial satellite galaxies. It is visible from Earth's southern hemisphere and is much more massive than the small dwarf satellites that barely disturb the galaxy. For a long time, models of the Sagittarius stream could treat the Milky Way as the dominant gravitational system and regard most other satellites as minor details. That assumption became harder to defend as estimates of the LMC's mass increased. A massive LMC does not quietly circle the Milky Way without affecting anything. Its gravity pulls on the galactic halo. It pulls on other satellites. It pulls on the Milky Way itself. That last part is easy to forget. We often imagine the centre of the Milky Way as a fixed point with smaller galaxies orbiting around it, but gravity works both ways. The Milky Way pulls the LMC pulls the Milky Way. Because the Milky Way is much more massive, its motion is smaller, but it is not zero. The result is that the reference frame astronomers use to describe Sagittarius is itself responding to another massive satellite. This can shift the apparent orbit of the stream. When researchers began including the LMC in models, some of the strange demands previously placed on the Milky Way's dark matter halo became less severe. Work modelling both Sagittarius and the Magellanic Clouds showed that the LMC's dynamical effect could not simply be ignored when using the stream to infer the outer halo's shape. This is a useful example of how dark matter research actually works. Astronomers did not measure the stream once and receive a neat answer saying, "The halo has this shape." They built a model. The observations disagreed with parts of it. They changed the model. More data arrived. Another massive object turned out to matter. The interpretation changed again. That is not a failure of the method. The stream is sensitive enough to reveal that the gravitational environment is more complicated than the original assumptions. Gaia has made that environment even harder to pretend is simple. Precise stellar motions show that the Milky Way's halo is not just a perfectly smooth, symmetrical collection of stars moving around an undisturbed centre. The outer galaxy contains streams, satellite galaxies, merger debris, and responses to massive companions. ESA has described the Milky Way's halo as elongated and tilted rather than behaving like a simple uniform sphere, while emphasizing that estimates of the galaxy's total mass still carry large uncertainties. Sagittarius helps because its debris reaches so far through that complicated region. A stream confined near the galactic disk mainly samples the gravitational field there. Sagittarius travels through a much larger volume. Its distant debris experiences the outer halo, where dark matter contributes a greater fraction of the gravitational field relative to the concentrated visible disk. That allows astronomers to probe the galaxy in regions containing comparatively few luminous tracers. Suppose one portion of the trailing arm reaches a large distance from the galactic centre. Gravity slows its outward motion. Eventually the stars reach apocenter, the farthest part of that orbit, and begin moving inward again. Where that turning point occurs depends partly on the amount of galactic mass inside the orbit. Add more mass and the gravitational potential changes. Remove mass and it changes again. The location and velocity of distant stream stars therefore help constrain how much matter exists far beyond the Sun, not perfectly, but measurably. The leading arm supplies another constraint. The 2 arms did not leave Sagittarius with exactly the same orbital energy. They travel through different regions and reach different turning points. A useful galactic model must explain both. The positions of those opposed centres, combined with stellar velocities and proper motions, help researchers test the Milky Way's mass distribution over enormous distances. That is important because measuring the total mass of the Milky Way is surprisingly difficult. You might think astronomers could simply count all the stars, calculate their masses, add the gas, include the central black hole, and finish before dinner. That would measure only the visible components reasonably well. The dark matter halo dominates the uncertainty. Different methods can produce noticeably different estimates of the Milky Way's total mass, especially because we're trying to measure a diffuse halo while sitting inside it. Even with Gaia, estimates remain broad, and different assumptions about the motions of halo objects can affect the result. Sagittarius provides one of several independent approaches. Globular clusters provide another. Satellite galaxies provide another. The motions of halo stars provide another. The galactic rotation curve provides another. Researchers compare all of them. If several methods point toward the same range of masses, confidence increases. If they disagree, somebody gets another research project, probably several people. The stream can also tell astronomers about how smoothly the dark matter is distributed. A simple picture of the halo treats dark matter as a continuous cloud. On very large scales, that approximation is useful, but the standard cold dark matter model predicts that halos should contain smaller concentrations of dark matter as well. Large galaxies form through a hierarchy of structure. Small dark matter halos form. Some contain gas and stars and become visible dwarf galaxies. Others may remain too small to form many stars. When larger halos merge, many of these smaller dark structures can survive inside them as subhalos. That produces a fascinating possibility. There may be dark matter structures orbiting the Milky Way that contain very few stars, perhaps none that we can detect. A dark satellite is inconvenient to find with a telescope because the normal strategy of looking for light encounters a fairly obvious problem. But gravity still works. If a compact dark matter subhalo passes near a stellar stream, it can disturb the stream's stars. Imagine a long, organised line of stars moving on related orbits. A massive object passes nearby. Stars closest to the encounter receive slightly different gravitational kicks from stars farther away. Over time, the disturbed region can stretch. A gap may develop. Density can pile up elsewhere. The stream may bend. Velocities may shift. By studying those patterns, astronomers can potentially infer the presence of an object that never emitted detectable light. Stellar streams are therefore sometimes described as detectors for dark substructure. Thin streams produced by globular clusters are especially useful for this purpose because they are dynamically cold and narrow. A small gravitational disturbance can stand out clearly against their otherwise organised structure. Theoretical work has shown how repeated interactions with dark substructure can leave measurable density and velocity signatures in stellar streams. Sagittarius is somewhat different. It came from a dwarf galaxy rather than a small globular cluster. The stream is broad. Sagittarius itself had a substantial internal velocity dispersion. Its debris has been created over repeated passages. The Large Magellanic Cloud perturbs it. The Milky Way disk perturbs it. The galactic bar can matter. Different wraps overlap. This makes Sagittarius less like a delicate thread that records every tiny gravitational tap and more like a very large probe of the overall gravitational structure. So when astronomers want to search for small dark matter subhalos through narrow gaps, they often turn to thinner streams. Sagittarius is especially valuable for the larger scale questions. How massive is the Milky Way? How does that mass change with radius? What shape does the halo have? How strongly has the LMC displaced the galaxy? How has the orbit of a massive dwarf evolved through the halo? These questions are connected to dark matter, even when Sagittarius does not provide a simple answer. There is another dark matter story attached to the dwarf itself. Before the Milky Way began dismantling Sagittarius, The dwarf probably possessed its own dark matter halo. That halo would have extended farther than most of its visible stars. Extended material is more weakly bound. So during tidal stripping, much of Sagittarius's dark matter could have been removed before the more concentrated stellar population was heavily disrupted. This means the dark matter debris associated with Sagittarius need not occupy exactly the same narrow region as its visible stellar debris. Numerical simulations have shown that a Sagittarius dark matter stream can be broader than the stellar stream and potentially offset from it. Some studies have even explored whether such debris could influence the expected signals in experiments on Earth designed to detect dark matter particles directly. These predictions depend strongly on the assumed history and nature of Sagittarius, so they should not be treated as a confirmed dark matter stream passing through the solar system, but they demonstrate how the dwarf's destruction could redistribute invisible matter as well as stars. The idea is worth considering because it changes the usual mental image again. When we say the Milky Way is eating Sagittarius, we tend to picture stars being added to the larger galaxy. But if Sagittarius originally possessed a large dark matter halo, the Milky Way has also been absorbing that. The merger combines invisible structures as well as visible ones. The stars are simply easier to trace. Dark matter stripped billions of years ago can become mixed into the Milky Way's halo without providing an obvious luminous marker. The stellar stream gives us a partial guide to that process, not an exact map. The dark and stellar components do not necessarily respond identically because they began with different spatial distributions inside the dwarf. Still, the surviving stars tell us where a dark matter-dominated satellite travelled and how strongly the Milky Way acted upon it. This connects Sagittarius with the larger theory of how galaxies form. The dark matter model used in modern cosmology predicts that large halos grow partly through mergers with smaller halos. Ordinary matter falls into these structures. Some halos form galaxies. Those galaxies merge. Their dark matter halos merge as well. A large galaxy like the Milky Way should therefore have a dark halo assembled from many earlier pieces. Sagittarius is one of those pieces arriving late enough for us to see part of the process. Its stars show the visible side. Its lost dark matter represents an invisible side that models must reconstruct. Earlier mergers are much harder to isolate because their debris has had more time to mix. Sagittarius has not yet finished mixing. That makes it unusually useful. There is still a core, there is still a stream. We can still calculate an orbit. We can still compare the positions of its debris with simulations. We're effectively observing one contribution to the Milky Way's assembly before the evidence has been completely erased. This also explains why astronomers are cautious when turning Sagittarius into a measurement of dark matter. The stars respond to all gravity. They do not distinguish dark matter from ordinary matter. A strim star feels the Milky Way disk. It feels the bulge. It feels the dark halo. It feels the large Magellanic Cloud. It can respond to other satellites and to changes in the galaxy over time. When researchers say Sagittarius constrains dark matter, what they mean is that they model the visible mass as well as possible, include other important gravitational influences, and then determine what additional mass distribution best explains the observations. Dark matter is inferred from its effects. That is why improved information about ordinary matter can change a dark matter measurement. If astronomers revise the mass of the galactic disk, the amount of dark matter required in the same region may change. If the LMC is more massive than assumed, some motion previously attributed to the Milky Way halo may actually come from the LMC. If Sagittarius itself began more massive, dynamical friction alters its history. Everything must be fitted together. The result is not a simple photograph of invisible matter. It is a gravitational reconstruction. And Sagittarius has already shown how sensitive that reconstruction can be. A stream that initially looked as though it might provide one clean measurement of halo shape instead revealed that the Milky Way's outer regions are dynamic. The large Magellanic Cloud matters. The galaxy responds to its satellites. The halo may not align neatly with the disk. Total mass remains uncertain. Different generations of Sagittarius debris have experienced different versions of this environment. The complication is scientifically valuable, because dark matter is not supposed to be studied in an imaginary quiet galaxy. It has to explain the real one. The real Milky Way contains disturbances, it contains mergers, it contains satellites, it contains tidal debris. A successful model of its dark matter halo must work with those facts rather than remove them for convenience. Sagittarius gives astronomers an enormous set of stars that have been testing that gravitational field for billions of years. Their locations are the results, their velocities are the results, their distant turning points are the results, their orbital plane is the result. The differences between older and younger debris are the results. We cannot see the dark matter pulling on them. We can see where they went, and the more accurately those stars are mapped, the less freedom the invisible galaxy has to hide its shape. That brings Sagittarius into an even larger pattern. The Milky Way did not obtain its halo through one merger. If the Milky Way is dismantling Sagittarius now, how many other galaxies has it already done this to? If Sagittarius is only one of those pieces, then the Milky Way begins to look very different from the stable spiral galaxy we usually imagine. It is still a spiral galaxy, of course, with a disk, a central bar, spiral structure, gas clouds, star-forming regions, and the rather convenient solar system sitting inside one of its quieter neighbourhoods. But none of that means the galaxy grew peacefully. The Milky Way was assembled. Some of its stars formed here, others did not. Some were born inside smaller galaxies that once existed independently, orbited through space for billions of years, and eventually found themselves inside the gravitational territory of a much larger system. Their galaxies were stretched, stripped, mixed, and absorbed until the stars became part of the Milky Way. Sagittarius is unusual mainly because we have arrived in time to catch the process halfway through. Many earlier victims are already gone. The phrase galactic cannibalism is often used for this kind of growth, and it is dramatic enough to sound as though astronomers were trying to improve the title of a documentary. But it describes something quite ordinary in the evolution of galaxies. Large galaxies grow partly by absorbing smaller ones. This is expected in the standard picture of cosmic structure formation. Small concentrations of matter form first. They merge into larger systems. Those larger systems continue interacting with other objects. Dark matter halos combine. Gas falls inward. Stars are added. Galaxies become larger through a mixture of internal star formation and external accretion. The Milky Way is not an exception. Its present size is partly the result of things it consumed. Sagittarius is simply one meal that has not yet finished. The evidence for older mergers appears throughout the galactic halo. A halo star can look completely ordinary until its motion is measured. Then it may turn out to be moving on an orbit, unlike stars born in the main Milky Way disk. Add chemical information, and the distinction becomes stronger. A star formed inside a small dwarf galaxy can carry abundance patterns produced by that dwarf's slower and different history of chemical enrichment. Combine enough unusual stars and astronomers can identify populations that once belonged to the same vanished galaxy. Gaia has transformed this work because it measured stellar motions on an enormous scale. One of the best-known examples is the ancient merger commonly called Gaia Sausage Enceladus. The name is doing several jobs at once. Gaia refers to the mission whose measurements helped reveal the population. Enceladus is the name given to the ancient galaxy. Sausage refers to the elongated shape its stars form in a particular velocity space plot, which is proof that even when reconstructing the collision of galaxies, astronomers eventually become hungry. The merger took place when the Milky Way was much younger. The incoming galaxy was substantial enough that this was not a minor disturbance like a tiny satellite dropping a few stars into the halo. Evidence suggests it strongly influenced the early Milky Way and contributed a significant population of stars to what we now call the galactic halo. Those stars are still here. The galaxy is not. that difference is important. A merger does not need to leave behind an intact satellite for astronomers to detect it. The stars can outlive the identity of the galaxy that carried them. Imagine taking several different jars of sand, each containing grains with slightly different properties, and pouring all of them into one larger container. After mixing, the original jars are gone, but if the grains retain enough distinguishing characteristics, you can begin separating the mixture statistically. Galactic archaeology does something similar with stars. The grains happen to be nuclear furnaces moving through a gravitational field, which makes the equipment somewhat more expensive. Gaia, Sausage and Enceladus is not the only population linked to accretion. Astronomers have identified structures and groups with names including the Helmi streams, Sequoia, Tamnos, and others whose exact relationships and origins are still being studied. Some may represent separate mergers. Some classifications can overlap depending on how researchers select stars in orbital and chemical space. The Milky Way's history is not a tidy family tree in which every stellar population comes with a clearly labelled ancestor. Different events happened at different times. Debris mixed. Later encounters disturbed earlier debris. Stars born inside the Milky Way can be pushed onto halo-like orbits. Accreted stars can become deeply mixed into the galaxy. Researchers have to distinguish all of those possibilities. Still, the broad conclusion is unavoidable. The Milky Way grew through mergers. Look at the galaxy now and you're looking at the accumulated result. That means the phrase Milky Way star can hide a complicated ancestry. A star can belong to the Milky Way today while having formed inside another galaxy. Ownership changes faster than birthplace. Sagittarius is currently producing exactly that population. Every star stripped from the dwarf becomes, dynamically, more connected to the Milky Way. Its orbit is governed primarily by the larger galaxy. Given enough time, the distinction between Sagittarius debris and the surrounding halo becomes less obvious. The same process that erased older satellites is operating again. This is useful because older mergers are difficult to reconstruct from their final state. We can see the archaeological remains, but not the original galaxy. Sagittarius provides a comparison. We know where the remnant is. We know where large amounts of its debris are. We can measure how quickly stars become distributed through the halo. That gives astronomers a living example of the mechanism that helped produce older structures. And while Sagittarius is being absorbed, the Milky Way is not simply waiting passively for additional stars to arrive. It responds. This matters because we often describe mergers from the perspective of the smaller galaxy. Sagittarius is stretched. Sagittarius loses dark matter. Sagittarius loses stars. Sagittarius loses gas. All true. But gravity acts on both participants. Sagittarius pulls on the Milky Way too. The difference is that the Milky Way is much larger, so the consequences are not catastrophic. They are disturbances. A disk galaxy can be disturbed in several ways. Its stars can be pushed above and below the main plane. The outer disk can become warped. Stellar orbits can be heated, meaning they become less orderly and gain larger random motions. Spiral patterns can be affected. Rings and density variations can develop. Gas can be compressed, potentially changing the rate of star formation. A satellite does not need to destroy the disk to leave measurable evidence behind. Think of walking across a thick rug. You are far smaller than the floor beneath it. You do not destroy the room, but the surface can ripple as your weight moves across it. Sagittarius has repeatedly applied a gravitational version of that disturbance to the Milky Way. The analogy should not be pushed too far because a galactic disk is not a rug, and Sagittarius does not have feet. Still, the idea of a large flexible system responding to a smaller moving object is useful. Computer simulations have shown that a Sagittarius-like satellite can excite spiral structure, influence the central bar, and disturb the Milky Way's outer disk. That does not mean every spiral arm exists because of Sagittarius. Galactic spiral structure can arise and evolve through several processes. The Milky Way has its own internal dynamics. The bar affects the disk. Gas responds differently from stars. Other satellites contribute disturbances. But Sagittarius is massive enough and has crossed the galactic environment often enough that simulations show it can be an important external influence. Gaia provided some of the strongest evidence that the disk has been disturbed relatively recently. When astronomers examined the positions and velocities of millions of stars, they found structures that should not exist in a perfectly settled disk. One famous pattern looks like a spiral when stellar height above the galactic plane is plotted against vertical velocity. It is often called the phase-space spiral, or, rather less formally, the snail. The stars are not physically arranged as a giant snail floating beside the sun. The spiral appears when their positions and velocities are plotted together. Its existence indicates that the disk is not fully phase-mixed. Something disturbed stellar motions, and those motions have been winding into the pattern we observe. Estimates from Gaia data placed a major perturbation within roughly the last billion years, consistent with the broad timing of a recent Sagittarius passage. That made Sagittarius an obvious suspect. It had motive, it had opportunity. It also happened to be a dwarf galaxy rather than a person, which makes the investigation easier in some ways and considerably harder in others. Later simulations have shown that the story is not as simple as assigning every local disturbance to Sagittarius. Some models struggle to reproduce all the details seen near the Sun using Sagittarius alone. The galactic bar, spiral arms, the large Magellanic Cloud, and internal disk evolution can contribute. Recent simulations continue exploring how direct Sagittarius perturbations and spiral structures triggered by the encounter may combine to produce the vertical waves and phase spirals measured across the disk. So it is safer to say that Sagittarius is an important contributor rather than declare it responsible for every unusual stellar motion in the Milky Way. Galaxies rarely provide one culprit. They prefer committees. The disk also contains large-scale density structures in its outer regions. One example is the Monoceros ring, an extended stellar structure around the outer Milky Way. Its origin has been debated, including proposals involving accreted debris and models in which disturbances of the galactic disk produce ring-like structures. Sagittarius interactions have been explored as one mechanism capable of generating outer rings and corrugations. That idea changes the way we think about a collision. The satellite does not need to leave its own stars everywhere an effect is observed. It can disturb Milky Way stars that were already there. A wave can move through the disk long after the object that excited it has moved elsewhere. This creates two different kinds of evidence from the same encounter. One is imported. Sagittarius stars form the tidal stream. The other is induced. Milky Way stars alter their motions because Sagittarius disturbed the disk. Astronomers can study both. The stream tells us what happened to the satellite. The ripples tell us something about what happened to the host. It is rather like reconstructing a ship's passage from both the material that fell off the ship and the wake it left in the water. Except the wake can persist for hundreds of millions of years. The disk is also not the only component that responds. Sagittarius moves through the Milky Way's dark matter halo. A sufficiently massive satellite can create a gravitational wake there as well. That wake contributes to dynamical friction, gradually changing the satellite's orbit. The halo itself can respond collectively to the passage, so the interaction includes stars, gas, dark matter, and the changing orbit of both systems. The phrase Milky Way eats Sagittarius makes the event sound pleasantly straightforward. The actual physics is more like the meal rearranges the dining room while being eaten. The possibility that Sagittarius influenced star formation makes the story even more interesting. We have already seen evidence for several periods of enhanced star formation whose ages roughly correspond to proposed Sagittarius passages. One analysis identified prominent increases around 5.7, 1.9, and 1 billion years ago. The interpretation is that repeated gravitational disturbances may have compressed galactic gas and helped trigger new star formation. This does not prove that every star born during those periods owes its existence to Sagittarius. Star formation happens for many reasons, but the timing suggests the dwarf may have repeatedly affected the conditions under which the Milky Way formed stars. That means some of the Milky Way's present stellar population may not have arrived from Sagittarius at all, yet could still exist partly because Sagittarius disturbed the gas from which those stars formed. There are two ways a merger can add to a galaxy: bring stars in, help make new ones. Sagittarius may have done both. This is one of the reasons galactic mergers are important far beyond the obvious act of combining two populations. Interactions reorganize galaxies, gas changes orbit, disks thicken, bars respond, spiral patterns change, star formation can rise or fall, central black holes in larger mergers may eventually become involved. The resulting galaxy is not simply Galaxy A plus Galaxy B. The collision alters the system while the addition is happening. Older mergers helped build the Milky Way in exactly this broader sense. Gaia Sausage Enceladus, for example, contributed stars to the halo, but evidence also suggests that the event strongly affected the early galactic disk. The young Milky Way that emerged afterward was not the same system that entered the encounter. This is what makes the idea of a finished galaxy misleading. Galaxies are temporary configurations, stable enough that our night sky looks nearly unchanged across a human lifetime, dynamic enough that billions of years produce something very different. The Milky Way has already consumed other systems. It is consuming Sagittarius now. It is interacting strongly with the Magellanic Clouds, and several billion years from now the entire local group will have evolved dramatically. The details of the Milky Way's eventual interaction with Andromeda are more uncertain than older textbook descriptions sometimes suggested because improved measurements of the galaxy's motions alter the range of possible futures. But we do not need to wait for that distant encounter to see galaxy evolution. The evidence is already above us. Some halo stars are fossils of earlier mergers. Some disk motions may preserve recent disturbances. Some globular clusters probably arrived inside dwarf galaxies, and one dwarf is still being pulled into a stream while we measure it. The word cannibalism can also make the process sound wasteful, as though a small galaxy simply disappears. It does not disappear. Its organization disappears. The stars continue. Its clusters can continue. Some of its gas may become part of the host. Its dark matter becomes incorporated into the larger halo. The original galaxy ceases to exist as a gravitationally distinct structure, but its contents remain part of the universe. Gaia Sausage Enceladus is gone as a galaxy, yet its stars pass through the solar neighborhood. A star can survive the death of its galaxy by billions of years. That will eventually happen to Sagittarius. Its identity is temporary, its material is not. The Milky Way's stellar halo may therefore be thought of partly as a collection of erased names. Each ancient satellite once had its own center, its own gravitational field, its own populations of stars, perhaps its own globular clusters, its own chemical evolution. Then the Milky Way changed the orbits of those contents until the original boundaries no longer mattered. Sagittarius lets us watch the boundary fading. We can still say that certain stars belong to Sagittarius because the stream remains coherent. We can still point toward a central remnant. We can still identify M54 near its center. We can still measure populations associated with the dwarf, but that distinction is weakening with every orbit. The Milky Way is not simply adding Sagittarius to a list of satellites. It is converting Sagittarius into Milky Way structure, and the more accurately we examine our galaxy, the more we discover that this process has happened before. Gaia's measurements have uncovered stellar populations that move differently from ordinary disk stars, revealing merger remnants that were hidden in plain sight. Some of those stars pass relatively near the Sun. Nothing in the night sky announces their extragalactic origin. You could look at one through a telescope and see an ordinary point of light. Its unusual history appears only after measuring its motion and chemistry. That is perhaps the strangest part of galactic cannibalism. A merger can stop looking like a merger. Wait long enough, and it becomes a galaxy. The Milky Way we consider our home is partly the aftermath of events that destroyed other galactic homes. The disk, halo, clusters, streams, and stellar populations all carry different pieces of that history. Sagittarius is adding another layer now. Its effect on the Milky Way will eventually become difficult to separate from everything that follows. Disk oscillations will mix. New stars will orbit for billions of years. The Sagittarius stream will spread. The remnant will weaken. Future disturbances will overlap the old ones. The event will move from something astronomers can watch in progress to something future astronomers would have to reconstruct archaeologically. That transition has already happened to most of the galaxies the Milky Way absorbed. It has not quite happened to Sagittarius. There is still enough left for us to call it a galaxy. The question is, how much longer that statement will remain true, because simulations of the surviving remnant suggest that Sagittarius may now be entering the last stage of the same process that erased those older systems. The remarkable thing is that the last stage may not require many more returns. Sagittarius has already survived billions of years of tidal stripping, repeated close passages, disk crossings, the loss of much of its original dark matter, the loss of stars over enormous distances, and the creation of a stream that wraps around the Milky Way. That sounds like evidence for resilience. In another sense, it is evidence that there is not much left to lose. The Sagittarius dwarf we observe today is the surviving centre of a system that was once much more massive and extended. Models of its original mass vary, partly because reconstructing a galaxy after severe disruption is difficult, but the progenitor is generally thought to have possessed a much larger dark matter halo and considerably more stellar material than the present remnant. Most of that larger structure is already gone. Some of it forms the stream. Some is likely much more widely dispersed. Some dark matter stripped early in the interaction may now be mixed into the Milky Way halo. The object still called the Sagittarius Dwarf Spheroidal Galaxy is therefore not a miniature version of the original galaxy. It is the part that survived longest. That distinction matters when we ask what happens next. A stable galaxy is held together by its own gravity. The stars inside it move, but their combined system remains gravitationally bound. A disrupting galaxy gradually reaches the point where the host's tidal influence is stronger than the remnant's ability to maintain that organization. Sagittarius is approaching, and according to some models may already be extremely close to that point. A detailed set of simulations published in 2020 focus specifically on reproducing the present Sagittarius remnant, rather than only matching the large tidal stream. Those models estimated a present total remnant mass of around 400 million times the mass of the Sun, with roughly a quarter of that in stars. More importantly for its future, the modelled remnant was badly out of equilibrium. Even its central density was too low to provide comfortable protection against the Milky Way's tides. When those simulations were extended forward, Sagittarius lost its remaining identity over roughly the next orbital period. The central concentration did not necessarily vanish instantly, but it stopped behaving as one gravitationally bound galaxy. In that set of models, the next billion years or so were enough to complete the job. That is not a universal countdown timer. We should not imagine a clock somewhere in Sagittarius reading 999,999,999 years and decreasing. Future disruption depends on the real mass distribution of the dwarf, its orbit, the Milky Way potential, and other details that remain imperfectly known. But the broad conclusion is difficult to avoid. Sagittarius is not recovering, it is being dismantled. Whatever exact sequence remains, its long-term future is integration into the Milky Way. The next strong passage will act on a dwarf already missing most of the structure that protected it during earlier encounters. This is why repeated tidal stripping can accelerate the final stages. During early encounters, the dwarf may have possessed a large dark matter halo. That extended halo absorbed much of the first damage. Its outer regions were stripped. later passages encountered a smaller system. Eventually, stars that had once been deep inside the progenitor found themselves closer to the new tidal boundary. Remove more mass and the gravitational well becomes weaker. Material that remained safely bound before becomes vulnerable. The process resembles peeling an onion only in the very broad sense that outer layers disappear before inner ones. An onion does not normally orbit a spiral galaxy at hundreds of kilometers per second, and for once we should probably be grateful. The surviving core has endured because its stars were among the most tightly bound. But tightly bound is not the same as permanently bound. If the central gravitational structure becomes weak enough, the next passage can unbind much of what remains. The stars will then spread along the orbit just as previous generations did. Another population will join the leading and trailing debris. The central density will fall. The object astronomers currently identify as Sagittarius will become harder to distinguish from its own stream. Eventually, there is no meaningful central galaxy left. That moment raises an interesting question. When does a galaxy actually die? There is no official event. No final star switches off. No explosion marks the loss of status. A galaxy can stop existing, even though nearly all of its stars remain perfectly intact. The thing that disappears is the gravitational organization. Today, Sagittarius contains a recognizable concentration of stars moving together around a center. After sufficient disruption, those stars will instead follow separate Milky Way orbits. They may remain close for a while. A density enhancement can survive temporarily. But if the population is no longer gravitationally bound as one system, the galaxy itself has effectively ended. The stars have not died. The galaxy has. That is a very different kind of destruction from most events we encounter in astronomy. A supernova destroys a star through an enormous physical event. A black hole can tear a star apart if it passes close enough. Sagittarius is being destroyed statistically. Its stars are redistributed. Its boundary loses meaning. Its internal orbits become galactic orbits. Give the process enough time and there is no clean moment left to point to and say, there is the dwarf galaxy. There is only debris. M54 may be one important exception to the general disappearance. The massive globular cluster lies near the center of Sagittarius and is much denser than the diffuse dwarf around it. Because M54 is strongly self-bound, simulations suggest it can survive after the Sagittarius galaxy itself is disrupted. That would leave the Milky Way with a dense stellar cluster that once occupied the center of a now-vanished satellite. Astronomers already suspect that some unusual globular clusters in the Milky Way may be the surviving nuclear remnants of earlier dwarf galaxies. Omega Centauri is often discussed in this context, although its exact origin remains an active research topic. M54 gives us a system where we can watch a similar possibility developing. Today it sits inside Sagittarius. In the future it may simply be a Milky Way globular cluster with a very complicated biography. This is how a galaxy can be reduced to clues. First, the outer dark matter halo disappears, then stars form streams, gas is removed, globular clusters are scattered, the central remnant weakens. Eventually, perhaps only a dense nucleus and chemically unusual populations remain recognizable. A future observer who never saw Sagittarius intact might have to reconstruct it from those pieces. We do something similar with ancient accretion events now. There is an interesting symmetry in that. Today, Sagittarius helps us understand extinct galaxies. In the distant future, Sagittarius itself will be one. The stream will also continue changing after the remnant disappears. A tidal stream is not a permanent frozen structure. Its stars occupy slightly different orbits. Those differences accumulate. The debris spreads. The leading and trailing structures continue wrapping around the Milky Way. Density contrasts become weaker. Features overlap. Interactions with the galactic disk. Dark matter halo, bar, satellite galaxies, and other gravitational structures alter the orbits further. Over billions of years, the once obvious Sagittarius stream will become increasingly phase-mixed. This does not mean every trace is lost immediately. Some dynamical structure can survive a very long time, especially in the outer halo where orbital periods are long. Chemical signatures can remain even after the spatial stream becomes difficult to see. A star's birthplace cannot be erased simply by moving the star somewhere else. Its elemental abundances can preserve clues about the environment in which it formed. That is why galactic archaeology remains possible long after obvious tidal tails disappear. The stream we see now is a temporary luxury. The debris is still organised enough that we can connect it directly to the parent galaxy. Future astronomers may have to work harder. They might identify a population of stars with related chemistry. Notice that some share unusual orbital properties. Connect a group of globular clusters. Find M54 behaving like a former galactic nucleus. Then reconstruct an ancient satellite that once travelled through the Milky Way. Their conclusion would sound very much like our reconstructions of older mergers today. Only we happen to know the satellite's name. There is more debris than the obvious stream already suggests. In June 2026, researchers reported spectroscopic evidence for a distant southern spur associated with Sagittarius, involving stars more than 80 kiloparsecs into the Milky Way halo. The population may represent some of the earliest stellar material stripped from the dwarf. That is important because those distant stars potentially preserve conditions from a much earlier stage of the merger, before Sagittarius had been reduced to anything resembling the present remnant. The farther we trace its debris, the more of the lost galaxy becomes available for reconstruction. Some stars removed earliest can now sit extraordinarily far from the core. Later stars occupy other wraps. The surviving centre represents only the latest stage, so when we ask where Sagittarius is, there is no longer one satisfying answer. Sagittarius is near the galactic centre as a remnant. Sagittarius is in the northern sky as tidal debris. Sagittarius is in the southern sky. Sagittarius is in distant halo structures. Sagittarius is in stars already detached so thoroughly from the dwarf that identifying them requires motion and chemistry. A galaxy that once occupied one gravitational system has been spread across another. The final unravelling will simply complete a process already mostly accomplished. The future stars of the dissolved remnant will not all travel together forever. Some will move ahead. Some will trail. Their velocities will differ. The Milky Way's potential will gradually disperse them. Future encounters can alter the debris further. The Large Magellanic Cloud and its evolving interaction with the Milky Way add additional gravitational complexity. Other satellites will move through the halo. The Milky Way itself will continue evolving, so Sagittarius will not become one permanent ring neatly marking where the dwarf used to orbit. The material will mix into a changing galaxy. This is what absorption really means. The Milky Way does not place conquered dwarf galaxies on shelves. It loses track of them. Their stars become part of its structure. Some are recognizable for a while. Some remain in streams. Some become part of the halo. Some clusters survive as compact objects. Their dark matter joins a much larger invisible distribution. Their gas, if retained long enough to reach the host, can mix with galactic material. After enough time, asking whether a particular region is Sagittarius or Milky Way stops being useful. It is simply Milky Way. Our galaxy has done this before. Sagittarius is useful because the conversion is incomplete. We can compare the living remnant with the debris. That provides information older mergers cannot give us. What does a satellite look like just before losing gravitational coherence? How do chemical populations move into tidal tails? Which clusters remain attached longest? How do multiple passages create separate wraps? How quickly does the debris phase mix? What happens to the Milky Way disk while the satellite is being destroyed? Those questions turn one dying galaxy into a laboratory for understanding galactic growth. The fact that Sagittarius is disappearing also removes a common intuition about scale. A galaxy sounds permanent. The word itself feels large enough to imply stability. A human life is brief. Civilizations are brief. Stars last millions or billions of years. Galaxies can survive for far longer still. But galaxies are not immortal objects. They are arrangements of matter maintained by gravity. Change the gravitational environment enough and the arrangement changes. Sagittarius was a galaxy before its current interaction reached this stage. It formed stars. It chemically enriched itself. It contained globular clusters. It possessed dark matter. It followed its own evolutionary history. Then its orbit brought it into repeated close encounters with a more massive neighbour. Nothing about its individual stars had to fail. The system failed. This is probably how many of the Milky Way's ancient contributors ended. Their stars did not arrive in one dramatic instant. The smaller galaxies were gradually disrupted until no separate object remained. Eventually, later generations of astronomers, had any been around, might simply have called those stars Milky Way stars. We are seeing the naming process before it finishes. There is also no reason for the Milky Way to remain unchanged after Sagittarius is gone. The disk will continue responding to past disturbances. Some motions will phase mix, others may persist. Stars whose formation was influenced by the encounters will continue orbiting. Sagittarius debris will contribute to the halo. M54 and other associated clusters may survive far longer than the dwarf. The destruction of the satellite therefore leaves permanent additions even after the obvious stream begins to fade. The Milky Way after Sagittarius will contain Sagittarius. That is the strange outcome of galactic destruction. The victim becomes part of the thing that destroyed it. Not metaphorically, physically. Its stars become Milky Way stars. Its dark matter becomes Milky Way dark matter. Its clusters become Milky Way clusters. Its history becomes Milky Way history. And because the process operates slowly, there is no single generation of observers that gets to see the entire event. The first close passages occurred long before humans existed. We are here during the late disruption. The final mixing extends into a future no human observer will personally reach. Astronomy connects those pieces by replacing direct experience with measurement. We find the old debris, measure the present remnant, simulate the future. The complete collision exists for us as a reconstruction. A few decades after Sagittarius itself was discovered, that reconstruction has grown extraordinarily detailed. In 1994, astronomers identified an unexpected moving population hidden behind Milky Way stars near the galactic centre. The object was elongated and already showed evidence of tidal disruption. Soon, researchers predicted that its stripped stars should form moving groups through the halo. Then those stars were found farther from the core. Surveys traced enormous leading and trailing arms. Infrared maps revealed debris across huge portions of the sky. Spectroscopy measured velocities and chemistry. Gaia supplied precise motions. Simulations reconstructed repeated passages. The stream became a probe of dark matter. The galactic disk revealed signs of disturbance. The dwarf that had remained unnoticed for most of astronomical history became one of the best examples of a galaxy being absorbed by another. And the story is still being refined. The distant debris discovered and studied now pushes us toward earlier stages of the interaction. Better measurements of stream stars improve the orbit. More detailed chemistry helps reconstruct the original dwarf. Future Gaia data releases will extend the precision and time baseline of stellar motion measurements, even though Gaia itself ended science observations in January 2025. Other surveys will add spectra for huge numbers of stars. Computer models will include more realistic versions of the Milky Way, Sagittarius, and the Magellanic System. The galaxy may disappear before the scientific questions do. There is one final scale worth keeping in mind. Sagittarius is being torn apart, but almost every star in the stream continues its ordinary stellar life. A star stripped 2 billion years ago does not care that its galaxy no longer holds it. Its core continues fusing elements. Its planets, if it has any, continue orbiting. From the perspective of something living near that star, the destruction of the galaxy might not look like destruction at all. The night sky would change over immense spans of time. The distribution of distant stars would shift. The orbit through the larger galaxy would evolve, but there would be no wall of Milky Way stars crashing through the local system. Galactic destruction is large enough to rearrange hundreds of millions or billions of stars while still leaving enormous empty distances between them. That may be the most useful correction to the dramatic title we began with. Yes, the Milky Way is tearing another galaxy apart, it really is, but it is doing so through gravity, across billions of years, by changing stellar orbits one population at a time. Sagittarius is not exploding, it is becoming the Milky Way. The long streams around us are the transition made visible. Each star in them marks a point where the smaller galaxy lost its hold. Together they outline an orbit, record repeated encounters, reveal the Milky Way's gravitational field, preserve the chemistry of a lost progenitor, and show us how large galaxies acquire the stars that later seem to have always belonged there. Somewhere inside that enormous structure is the surviving remnant, still moving, still losing material, still technically a separate galaxy for now. Around it are stars that left hundreds of millions of years ago. Farther away are older populations stripped during earlier stages. Perhaps beyond them are some of the earliest escapees, now more than 80 kiloparsecs into the halo. They all began inside the same evolving system. Gravity has simply separated their histories, and eventually the remaining centre will follow. M54 may persist. The streams will spread. The debris will become harder to recognise. Sagittarius will join the collection of galaxies that helped build the Milky Way and no longer exist as galaxies themselves. For a future observer, it may become an archaeological event. For us, it is still happening. So the next time you happen to look toward the Milky Way, assuming the weather, streetlights, and your own willingness to go outside are cooperating, there is no need to imagine our galaxy as a finished object hanging motionless in space. It is carrying evidence of ancient collisions. Its disk still moves in ways shaped by disturbances. Its halo contains stars born elsewhere, and around it stretches the debris of Sagittarius, a smaller galaxy being gradually converted into part of our own. There is no hurry to watch. The universe is taking its time. Sagittarius has been unravelling for billions of years, and the stars will continue their journeys whether we stay awake for them or not. For tonight, it is enough to know that beyond the quiet sky, the Milky Way is still growing, still changing, and still carrying the remains of galaxies whose stories have become inseparable from its own. And somewhere inside that much larger motion, Earth continues around the Sun continues around the galaxy, and millions of distant Sagittarius stars continue along the paths that first revealed what was happening. Slowly, silently, and with gravity doing nearly all of the work. Sleep well, fellow traveller.